RStudio until today. And what I want to say, and the purpose of this workshop, is that sort of to put a baseline and say, this is okay. That's one of the reasons, other than what Hui has already said about making all this knowledge open to the public, is to get everyone up to speed and comfortable with our Python, math, and generally data science workflows, and doing all this while opening this knowledge and skills to the broader public. Now, what I am about to share might be more relevant for some of you, but I hope that you will still find the beauty in it. And is that, in fact, over the years, I have collected some footage of our Hertie students in the Masters of Data Science encountering R for the first time, just to show you that you are not alone. So in here, you can see a Hertie student encountering R for the first time in the Intro to Data Science course, which you will have in your first semester. Here is a Hertie student trying to get their assignment for the causal inference course done. Here is a student working in their Bayesian modeling course. And what I am happy to say is that the model MDS student looks like this by the end of the first term. And this is very rewarding to see for us as instructors, this transition from maybe not being super comfortable with the programming component of the courses to having a very good set of skills that then you can carry on for the further semesters only within a span of months. And the purpose of this workshop, for those of you who are joining the MDS, and generally for all of those of you who are joining from all over the world, is to give you some skills that will make the transition between those two states simpler. So my expectations is that by the end of these 4 hours, you will leave this workshop looking like this. So some baseline knowledge that will make the process of getting into R in a smooth way. Now, we have broken down this 4-hour block into 2 blocks. So in the first session, we will start at a very slow pace. So we will effectively work on the basics and create a foundation. And then in the second block, we will build up at a faster pace on these foundational concepts. And then we will try to cover a broader set of skills, somewhat superficially, but to give you an understanding of what are the possibilities of things that we can do with R. So in the first sessions, we will start by going over R and RStudio, data types and structures in R. We're going to learn some basic commands or functions. We're going to learn some basic coding best practices. And my expectation would be that some of you may already know some of these things that we will cover in the first half. But I hope that by the end of the first block, you all feel that you have done a good, honest day of work. Now, in the second block, we will expand our skill set. And in this session, or in this part of the session, I will introduce you to the general philosophy of the tidyverse. We're going to learn a little bit about data manipulation with Dplyr and tidyr. We're going to learn about the grammar of graphics and plotting with ggplot2. And we will go over writing functions and iteration with per, depending on how much time we have. Something that I want you to keep in mind is that you all will have all these materials always available to you. There will be the recordings, so you can go over them on your own as well. And of course, it's to some extent difficult to learn programming within 4 hours. So the logic of this session is to give you a survey of what's possible, and then you can go back, do the exercises that we have, and try to build on those skills. So yes, at the end of the workshop, I hope that you will all appreciate R as much as I do, and get an idea of the capabilities of the programming language and can perform some data tasks. Now we can get started. So what is R and what is RStudio? So I imagine that many of you might have already gone over the pre-workshop announcement, and you might have noticed that you were expected to download 2 pieces of software, right? The first one was R, and then the second one was RStudio. So the first one, R, is a programming language. It was initially designed for statistics, data analysis, and data visualization. But now it is more than that. Thanks to a big community of developers, this is an open source piece of software. And people have contributed and extended the functionalities of this base language. Now, RStudio, on the other hand, it's what we call an IDE, so an integrated development environment. And in many of these introductory workshops that I have seen, people like to make to some extent a car analogy whereby R, so the software, the programming language is the engine, and RStudio, the IDE, is the car dashboard. So R is like the engine of the car. It is powerful. It does all the quote unquote real work and makes the thing move. But on its own, the engine is hard to control. It's not very user-friendly. And then on the other hand, RStudio is the dashboard and controls, right? So it's your steering wheel, your pedals, maybe your GPS in some cases, and it lets you interact and see what's happening. Now, in plain language, so in plain English, yeah, it will be our interface to R. Now, RStudio, this that we see right here, this is the default setup of RStudio, and it has 4 panels. So in this case, this can be modified, but this is the default setting. On the top left part, you have the editor. So this is where you can write and save your R code. So in here, you can have your script files, keep your code organized. You can have R files, the R markdown files. This is where the code that we're going to be working with today is going to live. Then we have the console, and this is a means to interact directly with R. So you type some code in there, you press enter, this runs the R code, and depending on what you type, you will get some output in the console. If you make a mistake, you might get an error message. So this is the means to interact directly with R. On the top right-hand corner, you have the environment, and the environment is an area that holds the abstractions of that you have created with your code. So if you were to run to create an object that is my result and is the result of 5 plus 3, it would keep there. It would have in here now my result, and it would have the number 8. And in the bottom right corner is the what I like to call the everything else. So this area is where the graphical output will be generated. This is where you will see a file panel to go through your files. You will find also menus for packages and documentation of the functions. And then this is generally the setup. Now, when we're working with R and RStudio, there are different ways in which we can write our code, in which we can write our code. So the most common way, and perhaps the one that you might see more in industry applications, is just basic R code. These are R scripts. They contain R code. Now, when we shift towards what we do, for instance, at the Hertie School, which is a policy school, we might care about the programming, but also the communication of insights generated from this code. So also thinking about a general data science workflow. And then we have in R and with RStudio 2 very flexible authoring frameworks that take both text and code. So the first one is a quote unquote relatively new addition. It's called Quarto. And then the second one, which we will be using in the workshop, is called R Markdown. Now, what you will see when we open the files that we will work with today is that these files look something like this, right? The R Markdown file is, or R Markdown generally is an authoring framework. And within this authoring framework, we can include code that can be executed and text. What this means is that we can generate all sorts of documents. So you can create websites with R Markdown, you can create slides with R Markdown, you can write books with R Markdown, you can write academic papers with R Markdown, You can generate, in fact, PDFs, etc., apps too. Now, the construction of an R markdown file is the most basic form has three pieces. So the first one is a YAML header. So it is a piece of code. It's a different programming language, and it scripts the way that the file should be compiled. So it has, for instance, the most basic form. We have a name, an author, a date maybe, and then it will tell the program, I want you to render this file as an HTML, as a PDF, as a Word document, as a Shiny app, etc., etc. Then you have these areas that have this gray hue right here, and these are what we call chunks, code chunks, and whatever lives within those bits is just executable code. The way they work is that they are living inside these accents. So you have three accents, curly brackets. So in this case, you have right here, the start of the chunk, three accents, curly brackets, the name of the programming language, in this case, R. You can also write Python. You can also write Bash. You can write any a wide range of languages. And then you close the code chunk with, again, the three accents. Whatever lives within those code chunks will be executed as code. And then finally, you have text input that makes this to some extent more flexible. And this text input can take simple, but very, again, sorry for repeating myself, flexible formatting. So you can input HTML or Markdown text in here. Now, why learn R? Well, R is free and open source, and this means a couple of things for us. A, there are no expensive licenses, so anyone can use it, and that goes along the lines of the mission of this summer school, right? This is promoting data access, equity access to data tools. A second reason is that R is widely used across sectors, so you will see R being extensively used in IOs, in industry, in government. This means A, that you can collaborate within organizations, you can collaborate within teams, but B, that when we think about you all as prospective data scientists, your skills are transferable across sectors. Third reason that is important for us as policy adjacent people is that it is a programming language, thanks to all the extensions that have been built over the years, that makes communication of results from a data science pipeline easy. So you can combine code, data, and a narrative to your data analysis. And you can publish this analysis in multiple forms. So again, as I said before, you can create websites, you can create dashboards, you can create apps, you can create just static documents, Word documents, PDFs, etc., etc. Now, it is also tailored for data work. At the core, it is a language that was built by statisticians. But those base functions then allow for an extension that make data analysis very easy. And we have a big community that has extended the capacity of the language to a suite of packages that allow us to do data science in a very streamlined fashion. So you can do data manipulation with a package, you can do data visualization with a package, you can do spatial analysis, statistical modeling, and there is a package, there is a set of functions that someone has written already for every step of the data science workflow. Now, what do I mean by the workflow and what do we mean by data science? Well, there is no consensus on the definition of data science, so we can take a look at what Wikipedia has to tell us. And it says that data science is an interdisciplinary academic field that uses statistics, scientific computing, scientific methods, processes, algorithms, systems to extract or extrapolate. Well, you can read the definition. We can think about this in plain English as data science is about turning messy data into useful knowledge to describe, explain, or predict something that's happening in the world. Now, among the most general conceptualizations of data science, they point to this junction of knowledge in statistics. So this is inference, uncertainty, modeling, knowledge in computer science. So this is programming, efficiency, scaling, and domain expertise, which you all might have. So this is knowing the context, the relevance, and the impact in your companies, in government, if you're working in a ministry, in your ministry, in your unit, and being able to leverage these three sets of core tenets, it's very powerful. Now, what do we mean when we speak about the data science workflow, and how generally a project workflow looks like, how R comes into it? Well, there is a phase that is detached of any programming in any project or any task, and this is your preparatory work, right? Defining your problem and task. If we're working with data, this can look like something like, okay, do I want to predict, infer, describe? Designing generally your data science pipeline, so conceptualizing, maybe building a data collection device, running the data collection itself, so recruiting participants, uh, parsing data from the web, monitoring that this is working, right? Then there are the data operation portion, right? So this is on a first part, maybe wrangling data, right? So this is importing data, tidying it, transforming it. Then there is the exploration part, so visualizing, describing, discovering it, trying to get a sense of what is inside our data. And then a part that we won't touch on the workshop today is modeling, so building, text, testing, inferring, predicting. And then a part that we will talk about today is also the dissemination part of these workflows, right? So communicating, be to the public, to your superiors in your company, to media, to policymakers, publishing in journals, proceedings, blogs, software, a website, and making your own products, right? Building your usable, robust, scalable apps that you can use in your company. Now, a key meta skill for the whole workflow is programming. What I advocate is that programming in R is one of the best skills for this workflow, because there are multiple solutions for every stage of the workflow, right? We have a suite of ready made functions that can just make our work easier. Now, what we're going to do now is move to R, and I'm going to show you what R allows us to do. For those of you who have already downloaded the files, you can go in the files. For those of you who have not done so, there is a Dropbox folder. You can just go into the tiny URL, and then the landing part is ds3-r-files. I'm going to give you all 30 seconds to do so. You download the folder, the whole folder. It's going to download as a zip file. You can just uncompress it on your, for those of you who are working on Mac OS, you just double click the zip file. For those of you who are working on Windows machines, you right click and then go to unzip. Once you have done this, the folder will look like this, more or less, right? So you will have 4 folders within that folder, and then one file that might look weird. It is an R project file. Go on and double click it and open it. It should open RStudio. Once you have done that, you will see, yes, you have a question?
Hello. Hello.
Yeah.
Can you hear
Yeah,
me?
hello.
Please also share the link in the chat. I can't get the link to the folder.
Yes.
Thank you.
I think that Hui or Leah can do this. The link is here.
This is share in the chat, Sebastian.
Okay, excellent. Thank you. Okay, so once you have downloaded and unzipped the file, you can go on and open the R project file. It will automatically open an RStudio session for the project. Then you can go on and on the bottom right-hand panel, click on scripts. And then in there, you're going to have the two scripts for each one of the independent sessions. So on the top, we're going to work on the first one. This is going to be the basic script. And then the last bit that you need to do is to click up here on the visual version so that we can get a more user-friendly version of the code. And you should have something like this at that point. For those of you who did not download R on RStudio, this is totally fine. You can do this at your own pace later. And what you can do is instead in the folder, you can go to the HTMLs folder and open the 01 DS3 basics HTML file. This will open in your browser and it will be a little website tutorial that you can follow through while I'm presenting. Also, the solutions will to the activities will live in these HTML files. So now what I suggest is that we move to R. Okay. So again, like we have now roughly 3 hours and a half, and what we will be doing in these 3.5 hours is build a strong foundation in R. The idea is to have a relatively short first session where we go over the basics, and then in the second session we're going to see the tidyverse, and in the tidyverse we're going to learn about a couple of different things so that we can understand the capacities of the programming language. So what we will do in this session is go over RStudio, take a look at how this looks, right? Get a sense on how we go about running lines of code, how do we go about maybe solving some issues, installing packages, running functions, etc. We're going to learn about the most basic building blocks in R. So these are the different data objects and structures and data types, and talk a little bit about best practices in R. So as you can see, this is the RStudio interface. In this case, I have a part minimized, but what you have here is the default display. So you have on the top left corner, you have the script editor. On the bottom left, you have the R console. On the top right, you have the environment and history. And then on the bottom right, you have the everything else, plots, help, files, and so on. So on the console, this is the means to interact directly with R. So if I want to type code here, it will run R code. So depending on what you type, you might get output or you might get an error message, right? Then you have the script editor, this area right here where we have our files. This is where you want the code that you care about to live. In fact, for many of you, those of you who will be enrolling in the Masters of Data Science in a month from now, this is where your assignments will live. Then we have the environment, and this is an area that holds our abstractions. And then finally, again, the everything else, where you will have your plots rendered, where you can ask questions about different functions, where you can go and take a look at your files. Then, so one of the first things is that learning R is, of course, not easy. It's effectively learning a new language. It's equivalent, I think, to learning a foreign language. And something that we have to keep in mind is that the key to learning language is practicing. So the way we learn R is likely by doing, and our best friend for learning a programming language is Google or any search engine that you use for that matter. What we can provide you right here during these workshops is some basic overview of R and how it functions, but you will only really learn how to program by actively using it yourselves. So it's something that I would encourage is that you go into this, you start playing with it, you start maybe thinking about smaller data projects that you want to work on from conception to the end. These can be little things like maybe looking at some data from the World Bank and maybe creating a plot. You can sit down a couple of hours, download the data, and try to work through all the pipeline of the data science workflow. And then what you can do is as you start working with R, you can ask questions since most of the use cases that you will have, we will be working for the most part with common packages, and you will be working for the most part with common packages. The errors, the questions that you might have, they are likely questions that many people already had, and when you Google, you will find likely the first answer to those questions in pages like Stack Overflow or blog post, the forum of Posit or RStudio, what was RStudio now, the Posit forum, and people will explain what's happening while you are encountering this code, what you can do to move forward. Yeah, I think that someone has their hand raised.
Shraddha, you can unmute and ask your questions. But if not, then you can also put your question in the chat. Thank you.
Okay. Yeah. We see that you're unmuted, but we cannot hear you. So it might be that you have not given access to your microphone to Zoom, Shraddha. Okay, maybe we can wait for the question to come in the chat and we can continue. Now, since R is an open source language, there are many free comprehensive guides to R programming. One that I think would be very useful for you all and for this source works for people who are just starting with R, but also more advanced users, is this one right here, R for Data Science. And this is a book. The book, if you see right here, it is a book. It is written with R. So this is a package called Bookdown. And you have effectively a whole overview of everything that can be done with R for data science. Now, let's move to the more practical bits and let's start working with R ourselves. So this document that we see right here has different components. Again, as we said, it had the YAML header on the top. It has some text formatted with markdown and HTML. And in here, we have the code chunks, right? Whatever lives right here, it's code. And to run code in R, we can go about it a couple of ways. The first way is we can select the line that we want to do, and we can do either Control Enter or Command Return in Mac, and it will run the line of code, and then we will get the output. When you're working on our Markdown or Quarto documents and you have code chunks, you can also run the whole chunk by pressing this button right here, and it will run the code, right? So in this case, we are doing this very cheesy exercise that every introduction to any programming language has, and it's asking the computer to print hello world. Now, as I said in the introductory part, R is a statistical language, and some of the base functions of R are effectively building up R to perform a statistical analysis. So some of the basic things that you can do is just use R as a calculator, right? So you have operators such as the plus sign, minus, times, so multiplication, division, exponentiation, finding the square root, finding the absolute value. So we can do things like using R as a calculator, running this line right here. I would do Command Enter, and it would tell me, okay, well, 4 times 9 is 36. I can run the next line. This would be the square root of 144. And it would tell me, okay, this is 12. I can run both pieces of code at the same time by selecting them all. And it would tell me, okay, the first input that you gave me, the output is 36, and then the second output is 12. In addition to these sort of basic arithmetic functions that come already attached to R, you have logical operators. So these are sort of logical operations that will come in handy when we're trying to work with data, subset data, ask the computer do something if something is true, right? So you have things like X being less than Y, X being less than or equal than Y, greater than or equal to. We have a symbol for being exactly equal. It's two equal signs. We have a symbol for not equal to. So an inequality is exclamation mark and an equal sign. We have a symbol for not being something. So this is the exclamation mark and what something is. When we want to say something or something else, we have this vertical bar, something and something else. We can use the and sign. And finally, we have another logical operator that's in. So X is in a set of Y. And we will use this in a second to maybe start playing with our data, trying to get our data into form, trying to look at a data set and subsetting, extracting parts that fulfill some logical operations. So for instance, in this case, we can have a logical operation where we ask the computer, is 4 greater than 2? And it is going to tell us yes, 4 is greater than 2. We can also ask, is 4 less or equal than 2? And it is going to tell us, well, no, actually, it is not. And these logical operators are very helpful for any type of exploratory analysis when we're doing data cleaning, when we're visualizing, and we just want to work with different portions of the data. Now, the building blocks of our workflow in R are objects, and objects in R are information that we store. So the way it works is that we can save information into objects. We can name those objects whatever we want. And our recommendation when we're doing this is, of course, to avoid naming them the same way functions that we might be using are called, right? So we would not use sum or min or absolute to name an object, right? The way the objects are created is with this operator right here. If you see, it looks like a little arrow, right? Sometimes you might see an equal sign. So for those of you who program in other languages like Python, you might use the equal sign. In R, you can use both, but the general convention is to use this assignment operator right here. Now, the reason why we do this is because a lot of functions use the equal operator to assign values to arguments within functions. So the general logic is you use the assignment operator, so the little arrow, to assign and then leave the equal sign for everything that lives within the function itself. There are other things that are sort of very idiosyncratic to R. So the hashtag symbol is the shorthand for commenting code. So whatever is following the hashtag symbol won't be run. It's just commentary that you can put right next to your code. And then there are special characters that cannot be used to name. So there is this $sign or the percentage sign. They cannot be used in names because they have other functionalities in R. So say, for example, we wanted to save into our memory, our computer memory, in an object called result, the result of this division, so this fraction, 5/3. We would run this right here. And then if you take a look at the top right, now we have a value saved into our memory that is called result, and it is the result of that division, so 1.66666. We can also access the objects that we have saved in memory by just calling those objects, right? So now instead of running 5 divided by 3, right? Now this abstraction exists in our computer and we can just run result. And now we have 1.66666. Now, something that happens with R and generally with many programming languages is that they will run code sequentially. So if you have saved in your code result before and you write another code, a bit of code with result following that, this will write over that. So in this case, we have the subtraction, so 5 minus 3. And then if you take a look at the right part of the environment, when we run that, it will write over the result of that division, and now the object result will be 2. Okay. Now, what we see right here is what we call a scalar. So it's an object containing one value. And these values can take different forms. So there are different types, data types in R. And here are some of the most common ones that you will use often. So you have numeric values, right? These are numbers. It includes all real numbers. So this is with and without decimal points. So in R, as it's the case, it's not the case in other programming languages. In R, both integers and floating point numbers can fall under this broad numeric category unless you explicitly define it, right? So you can have 5 and 8.5 be a number, but you can also have a special case for a numeric value, which is just a complete number, right? So a number without decimals. And this would be in R, you would create it by adding the L suffix. So this would be 5, and this would create a data type integer. Now you have characters, and these are what in other programming languages you might know as strings, right? So this is text data, character data, and this is sort of common forms of data, right? Pieces of text, IDs, labels, anything that is alphanumeric that you don't want to treat as a number. Now, there are other data types that are common to programming languages. So you have logical data types, these binary forms of understanding, true or false, or ones or zeros. So you can have this in uppercase true or uppercase false. And this would be also the result. So for instance, the logical operations that you do, they would tell you something is true. It would return an object of data type logical. And then we have factors, and factors are used to represent categorical data. And you can think about them in different ways. They can be an order, right? So nominal, things like red, blue, green, or ordinal, like low, medium, high, and then we can arrange those factors within vectors. So let's take a look at the different objects. In here, we will create a numeric object. In here, we will create an integer object. In here, we will create a character object, a logical object, and a factor object. Now, if we take a look at the number, it will have, again, this is a decimal point. This will also create a numeric object, right? Unless you specify the L at the end, it will create a numeric object. To create an integer, you will type the number that you want to keep and then the letter L in uppercase. This will create an integer. Now, to create character objects, character data types, something that is important is to input the text inside quotation marks, right? So this will create a string. If you don't have the quotation marks, R will render an error because it will not know what to do with it. It will think that this is an object, and then is another object, A is another object, and string is another object. And since we don't have anything by the name of this, is A, and string saved in the environment, it is going to just render an error. Okay, now the logical object, again, it is the value true, and then the factor object has some additional bits, so it is saying low, and it has levels, right? So it can be low. We can put something else in here. It can be green, and then the factor will have the level green. Now, the factors will be handier when we start thinking about not only scalars, right? Not only single values, but vectors of values, right? You can see what class of object you're working with, right? So in this case, we can take a look at the numeric object, and it will tell us it is numeric. If we do 8, and we ask it what kind of object it is going to tell us it is numeric, right? If we do the character object here, it is going to tell us this is a character. Now, why do we think about data objects? Because these are the building data types, because these are the building blocks then to move into vectors. And then from vectors, we have our data sets that we can use for our data science needs. Okay, so now we have the next step, right? So we have the single data types that we can use to have these scalars. That's the most basic unit within R for objects. And then we can use those scalars to build more complex data structures, right? There are many data structures. So again, the most basic one is the scalar, the single value, but then you have a junction of these scalars, right? And this is the most basic form that you generally work with in R, and this is a vector. And the vector is a sequence of elements from the same type. So this can be a representation of ages of everyone enrolled in the course, right? So 30, 35, 42, 28, 25, etc. That would be a vector of ages, right? By definition, this vector needs to contain all values from the same data type. Then we have matrices, and this is a two-dimensional structure where every element is of the same type. We will not talk about them a lot during this introductory session. They are very important for the statistical computing, the ML applications in R. So you might encounter them when you're taking your more complex courses as MTSs, or if you're not joining Hertie and you're taking this introductory data science workshop because you're interested in getting into data science, you will certainly encounter this data structure when you're trying to perform tasks that maybe are aligned to your use cases. Then there are lists, and lists are like vectors, but they're way more flexible. We won't talk about them in much depth right now. We will see them in the next section when we think about writing functions, iterating over code, and so on. And the general logic of list is that they can hold items and elements from different types. So you can have something being a string, something being a number, something being a logical value, and then you can even have a list within a list, and you can have a list within that list even. So they're very flexible data structures. And then finally, we have data frames, which is perhaps the most commonly used data structure for data science, right? So you can think about them as these canonical spreadsheets, if you may, or data tables. And then in there you have, within R, data frames are just junctions of vectors. So you have one vector, another vector of the same length, right? So this tabular format, and each vector needs to be of the same data type, right? So you can have age of being a numeric value. You can have the names of every participant being a categorical character value. Maybe you can have the place you're joining from. So Berlin, Bogota, Colombia, New York, Shanghai, etc. And these could be factors. Now, so let's take a look at how we can work with vectors. And in here, we will meet one of the most basic functions, and it's the C function. So you have C, the parentheses, and whatever lives inside of it is what will be vectorized. So in this case, we're creating a vector. C stands for concatenate. So concatenate the numbers 1, 2, and 3, and this will create a numeric vector. So if we run this, it will create the vector 1, 2, and 3. And if we run this, it will save it now to our environment. And you see here, my numeric vector is a numeric vector, right? So it's of type numeric. It has 3 objects, 3 values, and they are 1, 2, and 3. We can create a character vector, right? So we have, again, the concatenate function. We have welcome, comma, everyone, and then this would be a character vector that would have 2 values, welcome and everyone, right? When we create this object, again, it will appear in our environment and it would say my character vector. It has 2 values, welcome and everyone. And each one of these vectors has different operations that can be applied to them, right? So for instance, we have this right here. This is length. And when we apply length to a numeric vector, it will tell you how many values you have, right? So when you do this, it will tell you, well, in that vector is of length 3, right? So it has the values 1, 2, and 3. If you do str stands for structure. CR will then give you a summary of what lives inside that vector, right? So it will tell you, okay, you have a character vector of size 2, and it has the following values. Okay, now we have matrices. Again, this is something that we won't go in very much depth, but this is the construction of a matrix. So what we're telling it is grab every number from 1 to 9 and input them in 3 rows and 3 columns. So it will create an object that looks like this, and it is going to be a matrix. And again, these type of data structures are super flexible. They are not very memory heavy, so they are one of the sort of data structures that make R for statistical computing very powerful. You might encounter them when you're taking, for instance, your Bayesian modeling course. If you decide to take that elective, you will encounter them if you go into an ML application with R. These data structures, these matrices, are very useful for statistical computing. And then these matrices also have some operations that we can perform in them. For instance, asking them, what is the dimension of my matrix? So in this case, it is going to tell you, you have a matrix that is 3 by 3, right? You can have lists, and lists are, again, these very flexible building block. So in here, we have a list that contains 1 numeric value, 1 character value, and a logical value. And if you take a look at the list that you have created, it has the number, it has the character, and it has the logical value. And you can access these by indexing, which we will learn a little bit more in a second, right? So you can start getting these values. You can store data in lists and then use different portions of those data. Now, again, the most common form that we will use when working with data in R is likely going to be a data frame. The data frame, this one right here, is the base R data frame. When we move to the tidyverse application, there are other different ways to store data in tabular form. They're always going to be called data frames. And there are some data frames and some ways of storing data in R that are more memory efficient. So there are packages that will store data in a more efficient way. When you're working with millions of rows for your intro to data science project, maybe you might not want to save it as a data frame, but would want to save it as a data table. There are different packages, but the logic is very similar, and the syntax to work with these data tables is relatively similar. So in here, we're creating a data set that has some IDs. So they're going to be the first 10 letters of the alphabet. It's going to have a variable called X that is going to have all the numbers from 1 to 10. And then it's going to have another column, a variable Y, that is going to have all the numbers from 11 to 20. And then when we take a look at my DF that now was created in here, you can see that now we have a data set, data frame with 10 observations that has 3 variables, again, ID, X, and Y. And when we look at it, we can see the data frame right here, right? So it has A, B, C, D until J. It has the numbers from 1 to 10, and then it has on Y, it has the numbers from 11 to 20. Now, on these data frames, you can also have different operations that you can use to just quickly get an idea of what's in there. So for instance, one of the most common ones is head. And what head does by default is that it prints the first 6 values in your data frame, the first 6 rows, sorry. So in this case, it would be the first row, A111, second row, third row, and so on until the 6th row. You can also tell it, okay, I actually just want the first 3 rows. It will do that. If you do something like I want the first 7 rows, it will do so. And in here, you have a collection of some things that you might you do as operations to get a sense of what's in your data. So you have head, again, printing the very first rows. You have tail, giving you the bottom rows. You have dim, which is one that we have used, the dimensions, number of rows, number of columns. You can also use the structure function on data frames, and the names of the data frame. So it will give you the names of the columns. Now, in here, there is another, I see that Yang has his hand raised. You can unmute yourself if you want. Okay, I'll put your hand out. Okay. Now, again, like some more on factors. So we saw the factor as a scalar, and when we see the single factor, it does not really make sense. But when we think about factors as a junction of vectors, right? So we have in here a factor of marital status, right? So we have a person who's single, a person who's single, a person who's married, a person who's married, and a person who's single. And we turn this into a factor, then it starts to make sense, right? So we have a vector that has 5 values, right? So it has single, single, married, married, single, and then it has 2 levels, right? So as we start thinking about factors in this vectorized sense, they start to make sense. Something that you can do is have values in one data type. So in this case, what we can see here is that we have a vector that has strings inside of it, right? This vector, if we look at it, it will be of class character. And what we can tell it is use functions there are many of them. There are means to turn characters into numeric variables, and the general logic, the general syntax is the same. As dot what you want to turn it into. So in this case, we want to turn this vector that is a character into a factor. And what we would do is, again, as dot factor, and it would turn that into a factor, and then it will be a factor that has the married and single levels. When we go through these little portions of the session, you will see that there are these links to outside sources. Make sure that when you get some time, maybe explore them. There is a lot to be gained from exploring those resources. So again, we already saw vectors, and again, vectors are this building block. They are this one-dimensional array that represents a collection of information stored in a specific order from the same data type, right? So what we saw before is that to create a vector, we use this C function, the concatenate function, and then we input the objects of the same type in it, right? And then we can assign it to whatever you want to name your vector. So let's suppose we have data of the population of millions of the 5 most populated countries in 2024. So these are the data from the World Bank. And we have a country that has 1.45 billion, 1.4 billion, 440 million, 283 million, and 251 million. We can save this as population 1, so pop1, and then this would create that vector. So it will be stored here. We have pop1, it has these numeric values, and then it is the values that we have inputted there. Now, we can use the concatenate function also to combine 2 vectors, right? So in this case, we can use the top 10, right? And then this would be the following 5 countries, right? This would be population 2. And you can use C to then join these 2 abstractions, right? We don't have to type all these values again. In the memory of our machine, there is already the idea that POP1 stands for something, it stands for these values, and POP2 stands for something, it stands for these values. So what we can do is concatenate population 1 and population 2, and it will create the new population vector that is going to hold those 10 values. You can also do something like this, right? So the logic is that these objects that you create in R are just shorthand. They're little conventions for the abstractions that you have created, right? This is the equivalent of this right here, right? So you can also perform these operations in vectors. Now, so something that we can do is check the variable type of our population. So this data that we have just created, and when we run this str, so the structure, it will tell us, okay, you have a numeric vector. It has a length of, so it has objects from 1 to 10. So it has a length of 10, and these are sort of the first values, right? Suppose that we wanted to add information now. So we want to start building into this, and we want to add information about the country names. In this case, they're not actually the names, they're the ISO codes. And we want to enter this data in character format. So just for time saving, we will do this for the 5 most populated countries. So again, we have the concatenate function, we have the ISO code for the most populated country, and then each object, each value is separated by a comma. So India, comma, China, comma, USA, comma, Indonesia, comma, Pakistan. And then we can create that country name. That country name is going to be a character vector that we see now here, character vector. It has 5 values, right? So they're going to be India, China, USA, Indonesia, and Pakistan. Now we can now code logical variable that is going to show whether, or is going to hold this abstraction of whether the country is in Asia or not. So R recognizes both true in uppercase or an uppercase T as being true, and false and an uppercase F as false. So in this case, we're going to build this vector, logical vector Asia, and it's going to be India is in Asia, China is in Asia, the US is not, so it's going to be false. Indonesia is in Asia and Pakistan is in Asia. And now we have our string. So it's true, 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 false, true, true. Now, what we're going to finally do is going to define a factor variable with the regime type of the country. So we're going to use this data from the Economist Intelligence Unit. And in their data, a country can be a full democracy, a flawed democracy. It can be a hybrid regime, or it can be an autocracy. So if you take a look at these countries that we have, so India, China, the US, Indonesia, and Pakistan, we don't empirically have a full democracy nor a hybrid regime, quote unquote. So what we can do is define empty factors for those levels if we want. But in this case, we can just keep this here. And what will happen is that it will just say you have two levels, either you have a flawed democracy or you have an autocracy, right? So according to the Economist Intelligence Unit, there is India as a flawed democracy, there is China as an autocratic regime, there is the US as a flawed democracy, Indonesia as a flawed democracy, and Pakistan as an autocracy. And then now we have this, which is a character, right? And then what we're going to do is, again, what we spoke about before, right? So in this case, we have a string. We can turn that string of a vector of strings into a numeric value. And what we're going to do is turn this regime into factors, right? So we're going to use the asFactor function. And if you see at the moment, regime is a character that has the flawed democracy, autocracy, flawed democracy, autocracy. And we're going to turn it into a factor, right? And if we take a look right here, then now regime is a factor with two levels. Those are the two empirical levels we observe, right? Either flawed democracies or autocracy. And then it is saving each one of them, autocracy, flawed democracy, in that data set. We can also, for instance, change the logical vector into a character vector for some reason. Now it's a character. We can turn it back into a logical vector. Now, let's do a little exercise, and it's sort of like to regroup this section of like concatenating and thinking about these data types, data structures. Let's do a first exercise, and let's think all collectively about why would R not let us do any of the following. So if we ask R to do this, it will give us an error. And if we ask R to do this, it will give us, this right here, it will give us an error. Does anyone want to give it a go as to why this is not working? Yeah, so Ines says the quotation marks are missing, right? So yeah, the fact that the quotation marks are missing means that in this case, R is expecting that we have some abstraction. When we type it like this, it will think, or it will look, this will only work if we have something saved in here as one. If we were to save, for instance, in here, we would do 1 is 1, 2 is 2, and 3 is 3, and we were to run this, that would work, right? And now it is saving the abstraction, right? It is running that. But if we did not have those elements, what would be missing is the quotation marks if we wanted to, for instance, save this as a string, right? So if we wanted to save this as a string, this would work. Okay, so like I guess you all get the idea of what the difference between having the quotation marks and not having the quotation marks when we have something in natural language is. And is that when you don't have the quotation marks in your vectors and you have a word that to you might mean something, R is going to look for an abstraction in memory. So it's going to say, do I have something saved as A, B, and C in memory? And it's going to say, well, actually, I do not. And that's when it is going to give you an error that that it is going to tell you, well, actually, I have no idea what object A is. Yeah, so Orkun, all the solutions and all the bits of code that you will need for the activities are already in the HTML. So you can just copy and paste them in R and just work to some extent fast. Now, what's going to happen here? So what's the difference? What's the difference between these two and what's going to happen there? So if we were to run this, what do you think is going to happen? So we have in here a true as a logical, and then in here we have a true as a character. Yeah, so Pakitsa has said this. So Andres says that this will create a list. No, it will not, but that's a good guess. So in here, this is going to concatenate true as a logical and true as a character. And one of them is going to take precedence. And normally the one that takes precedence is the character. And then it is going to turn everything into a character, right? So in this case, div will be a character. If we take a look at div, it will be a character. Now, if we were to do this right here, then it will be a logical, right? So when you type one value from one data type and a value from another one, the character value is going to take precedence. So remember that a vector is always going to be by force of one data type, right? So if we were to have something like this, again, this will run, this will not give you an error, but it will give you a character 2 and a character true, right? So remember that the vectors are always by force. They're always by force of one data type. And if you have things that are ambiguous, R is going to follow a sort of a default behavior where it will leave it as where it will, like one data type is going to take precedence. So maybe you all know this one. What is the class of this following vector right here? So what type of vector do we have here? It's a character, right? So Pakitsa has said it's a character, right? So even if we as people, of course, we understand these to be representations in our natural language. These are representations of numbers. Of course, the programming language cannot know that they're numbers. And if we give it things that it will understand, which is effectively everything that you put into these quotation marks when you're creating a vector, I'm going to turn into a character. Well, it will follow the instructions that the program will follow the instructions that it has in its base code base, right? Now, you can also do vector operations now, right? So like that was a little bit of this exercise of making sure that we are all on the same page. And when you have these vectors that, again, all of them need to be of the same data type, we can do some operations. So we can do a variety of things. And this is where, things start to get a little bit more interesting, because then this is where we get to expand on these data structures. So we have very basic data, so the one value, the scalar, then we have vectors, then we can have a combination of vectors that can be a data frame, and you can do operations on those vectors, right? So say, for instance, we have the population of the top 5 countries right here, so like the population of India, China, US, Indonesia, and Pakistan, and say we want to ask ourselves, what would be the population of those countries if it were to double in X years, right? So you can do these arithmetic operations that we had seen at the start of the session, right? And you can say, okay, grab those numbers and multiply them by 2. And what this will do is give us a new object that we have created, population1 doubled, and it will tell us, okay, for the first value, it will perform that task on the vector. So it would do first object in the vector, first value in the vector times 2, second value in the vector times 2, third value in the vector times 2, and it will tell us, okay, we would observe 2,902 for India, so 2.9 billion, 2.8 billion, 880 million, and so on. So you can start playing with these things. Now, what do you think this will do? So we have the vector population 1, and then we have the vector population 2, which was the top 5 and the 6th to 10th position in this. What do you all think this will do? So Shreya said it will append both population 1 and population 2, and that's exactly the answer that I was looking for, because that's exactly what would happen in other programming languages, right? So in other programming languages, when you do this, you would get this result. So the concatenation, it will just concatenate the population 1 and 2. In R, this is not the case. So what it will do is exactly what Sophia is saying. And what Sophia is saying is it will add these values, those 5 values, to these 5 values, and it will add them in that order, right? So when we run this, it will add the population of the number 1 country, so the top populated country, to the one of the 6th, the second to the 7th, the third to the 8th, the fourth to the 9th, and the 5th to the 10th. So for those of you who are used to programming in Python or other programming languages, just be aware that in R, this will not concatenate, but these arithmetic operations will work as mathematical operations. And in there you start seeing that at the core of R is a programming language that was initially devised for statistical analysis by statisticians. Right? So when you want to append, you would need to use this, again, the concatenate function, the C function. Okay, now I have been sort of implicitly using them, and we have been implicitly using them, but we have not spoken about functions. And functions are sort of these already reusable pieces of code to perform specific tasks. So I've seen in many workshops, people call them little tools or machines, right? Like you grab the hammer, and the hammer is has a method to, or like the hammer is useful for one thing, and it's to pin nails, right? And then it takes some arguments, right? So like there are these analogies of functions being tools. There are also functions thinking about machines, right? So you give them an input, they give you an output. And each one of these functions is designed to perform a specific job, right? So in this case, the concatenate function, the C function, is designed to perform the function of concatenating things. In fact, this plus sign is a function, and it is a function that is designed for a specific job, and it is to add. Now, so in the same way that you would use, again, the screwdriver to tighten a screw or untighten it, you can use, for instance, min to calculate an average, or length to count elements. And there are many built-in functions in R. These built-in functions, again, as I said before, this is a programming language that was written by statisticians in the most part. So the basic form of R, what we know as base R, these are, you download R, and all the prepackaged functions that come with R before you do anything else, those functions are going to be helping you analyze and summarize data for the most part. You don't need to do anything else. They will be already in your machine as you have downloaded R. And this can be things like min, which the names tend to be very self-explanatory. So min will return the minimum value of an object. Max will return the maximum value of an object. Sum will return the sum of the values in an object. Length will return the length of the values, mean the mean, median the median, var the variance, standard deviation, or SD the standard deviation, right? So we have the population vector. So this one is the one with the top 10 values. And if we go to min, well, we would expect that it points this one out, right? So when we run min, it will give us, yeah, in fact, the least populated country within these 10 countries. It has 132 million inhabitants. Max would be the max. So the top, the highest value would be 1.45 billion. So this would be the value for India. And then with mean, we can get the average of these 10 numbers. So mean would give you the arithmetic mean. And then it would be 472.7 million. So we have seen this option to calculate the mean, the arithmetic mean. Can anyone think of a way in which we can compute the mean population from, so this is the information that we have. We have the 10 values, right? Is there a way that we can use any of these functions here to calculate the mean? So other than, of course, min pop. So alternatively, like we want to get to this number, but through other means. Okay, so Madhu just said it, right? So it would be summing the population, right? So this is how we get the arithmetic mean. This would be the sum, and then we would divide it by the length of the pop. So it would be the sum of all those values, which would be 4,727. So this is population in millions, right? So it would be 4.7 billion divided the total number of observations that we have. So this would be divided by 10, and it would give us again 472 million.7, right? So this would be how we would get an average, like the arithmetic mean, using other things. And this is just a silly exercise to A, get you familiar with the different functions, but B, to bring the larger point that when you're programming, there are multiple ways to get to the same result. And if you seed 10 coders, you will likely get 15 different solutions to the same problem. So this is just to illustrate that. You will get the answers, like I will share this again, like I have already pre-compiled the answers, and the answers to all this exercise where we are actually typing code, you already have in the HTML file. You can just press the toggle, click here for answer, and then it will drop down the answer, and you can copy and paste it into your R session if you want. Now, something else that we can do with vectors, and that is important for us, is of course, okay, we have a vector of 100 values. We might want to just access some of them, right? And when you have data stored in vectors, you might want to access it, modify it, remove some values, and so on, right? These are things that we do as data scientists. And in base R, the way we go about doing this, and it's very similar to the way you do it in other languages. I get the impression based on what I've seen in the chat on the answers that you have given to some of the questions that many of you already have some familiarity with other programming languages. So the logic is relatively parallel to the way you would go about indexing in other programming languages, with one difference for those of you who, for instance, know Python, right? So the way we access items, single elements within these vectors is with square brackets. So up until this point, it's very similar to other programming languages. So say we want to access the first element of our population one vector, right? We would just have square brackets 1. if we wanted to get the first element of our country name vector, we would do country name 1. So now I imagine that this is the part that you all who are working in Python are like, wait, what? So R uses 1-based indexing, meaning that the starting position is 1. It's not 0 like other languages, right? So I don't know if, for instance, some of you have been in the Americas and in Europe. We can think about this as the way floors work in the Americas versus Europe. So in Europe, this is the Python way, the ground floor is floor 0. In the Americas, the ground floor is the first floor, right? In R, the first element of each vector is 1, and then you start going from there, right? So to access the first element, for those of you who are familiar with Python, R uses 1-based indexing. Now, you can also combine this and use, for instance, this concatenate function and access multiple elements, right? So you can, for example, use indexing to explicitly print the second and fifth element, right? So you can have the indexing within square brackets and say, I want elements in positions 2 and 5, and this will print the second and fifth most populated countries, and this would print the second and fifth names of those most populated countries, right? So C in this case creates a vector of the indices that we want to extract, right? You can also grab those values that you have extracted and save them onto other abstractions, right? So say we want to create the object first. In here, we can extract that first value. And then in here, we see it is 1.45 billion, right? You can also use this indexing to remove elements, right? So this is also called what is called negative indexing, right? This the index -1. And then this would be something like, let's create a copy of the country names, and we can remove from our country name, say, grab everything, but that's what the negative indexing does. So grab everything, but the value on position 5, and what it will do is grab everything but that value. You can also do grab everything but 5 and 1, right? And it will grab everything but those values right there. So this is when we have this minus inside the brackets when we're indexing. This is negative indexing. So again, in here, we're telling it grab this value. In here, we're telling it grab these two values, right? In the bottom right here, we're telling it grab everything but this value. Now, something that we can do is use this negative indexing to remove information, right? So we can say from this right here, you can remove the last value, right? So we can also use the functions that we have learned to make this more more parsimonious, right? So say you don't know how long is your element, your vector, or it might change. Then you can say, okay, I just want the length. So the length is always going to be the last value, right? Just delete whatever is last and it will remove it, right? So in this case, what we can do is use length to achieve a level of generalization in the code that is not bound to us changing this value every time, but we can just tell it whatever is the length of that vector, grab that value and delete that last element, right? You can also use indexing to change values, right? To replace values. So for instance, in this case, we have that the US is a flawed democracy. And I mean, like when I prepared these materials, this was not the case, but now more and more this example actually resonates with reality and say that now we are working with this data and the US has gone from being a flawed democracy to an autocracy. So we can replace this value. So we can say on position 3 of regime, put autocracy. And now we have that regime number 3 is an autocracy, right? So we can use the indexing when it is on the left-hand side of the operation to change the values that are within the vector that we have, right? So when they are on the right-hand side, they help us extract values, right? When they are on the left-hand side, so what's being operated on, what we do in here is going to feed into those values. So say now we have made more mistakes when entering the data, and we realize that when, say, we're working for an international organization and we're working in headquarters and we have an M&E officer that sent us data that is off by 10 value, by a factor, but by 10, a number of 10, right? And this was only an error that happened for the third and fifth element of the population vector. How would we do it? So we want like to put this in plain English. We have this, and we want to subtract 10 from 440 and from 251. So the third and fifth element in this vector. How can we do it? So remember, like this is going to be a combination of assigning, right? So it's assigning is accessing multiple values, right? And then, well, like the operations perhaps, right? So I'm going to give you a couple of seconds to try to think about this. If not, I can also give you some hints. So again, it is about assigning, selecting multiple elements, and performing an operation. Okay, so Shreya tried to give it a go. So Yang actually gave us the answer right here, and maybe we can break it down all together, right? So this is the answer would be population 1 copy. Then we would index and we would say the elements that I want to write over are these ones, right? So then I want to assign some value to them, right? And this value is going to be those values minus 10, right? So if we take a look at just this portion right here, it will grab those values and subtract 10. And now our population copy has that, right? I want to tell you something. These exercises that we're doing with the indexing and so on, they're silly exercises. I still want you to be here with me, but in the second session, we're going to meet the tidyverse, and we're going to think about, okay, like that thing that we were doing before that made everything totally complicated. And now, after we have seen the tidyverse, everything makes sense. But still, it is helpful to know how base R is working, how base R is doing things, because A is the most stable way to work with R. So if you're working with, like, I don't know, for those of you who are in the Master of Data Science, you will likely, in, I believe it's the 9th session, you will have to write your own package. And then trying to keep things in base R will ensure that when you're writing your own packages, your package is stable and you're not depending on other programming not making changes, right? So this is how it would look like. And then in here in the exercise, actually, I made a note on a common mistake that could be something that people would like default to, and it's saying, okay, I am assigning something to this, right? So maybe I just say subtract by 10. But what's your intuition? What will happen if we do this? Does anyone have a guess of what will happen if we do this? Exactly. So what you just said, it will assign the values -10 to them, right? So like in this case, we are telling it what's on the right-hand side is going to get assigned to this, and then this would be wrong, right? So what we want to do is, again, tell it to this stuff right here, assign this -10, right? And then that's what we will do. Okay. Now, there are many more functions. There are millions and millions and millions of functions, right? So in here we have the sequence function. It will create a sequence from input 1 to 2 by input 3. There is repetition function. There is the names function. There is the which function. There are millions and millions of functions. There are packages that themselves have collections of functions. We will see some of them today. And then maybe let's take a look at this sequence function to get an idea of how functions work. So again, we said functions are these little machines. They are tools that are meant to perform some operations. They expect some things, and then they give us some things in return. So the function sequence expects some arguments, right? So arguments are the things that the function expects. Let me just go here, and we can take a look at what the function is expecting. So sequence. So if we take a look at here, this is like when you ask a question mark and put the name of a function, the documentation of that function will come in, and in here in the panel of the what we called everything else, things will appear, right? So it will say, well, sequence is a function from base. Here it will appear the package where this comes. So this is base R. This is just the things that come already prepackaged with R. And it says it will create a sequence. It will create regular sequences, and it will take these arguments. You can have from, to, by, right? So in here, we're doing it, and it will create the sequence, a sequence from 1 to the length of population 1, which is 5, by 1. If we wanted to do something else, we can do it by 2, and then it would create a sequence by 2, so it would do 1, 3, and 5. And this is one way of running functions with argument names. You can also run functions by argument order, right? So you don't have to always write from equals to equals by equals. If you know what are the expected arguments of the function, you can type the first argument it is expecting is from, the second argument that it is expecting is 2, and the third one is going to be the by these intervals that are happening. And then in here, we would get that, right? So these are two ways of working with functions. And then in here, we have another function. So this is repeat. Repeat by default uses in here implicitly times. So if we do not specify something else, it will run hello world, hello world, hello world. If we change the argument to be each, for instance, it would type hello, 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 and then world, 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 world. This is something that you can start to play with as you start seeing functions. There are other functions like names. So names is a function that helps us work with labels. In this case, say, for instance, we're going to create a new version of this data structure that is called a name vector. And what we're going to do right here is have the vector population 1, but we're going to give it names. So that population 1 now has the vector is going to be the numbers, but it will have a shorthand that will help us, for instance, to access values within it, right? So we can index with those names, right? So instead of saying, I want the one in the 5th place, right? So population 1 in the 5th place, I can just run where, like, extract where names of that equal to Pakistan, right? So should we do this activity? Access all top 5 population values that are greater or equal to the mean population, right? So we can do something like this, right? We have population 1, and what we want to do is extract all the population values that are greater or equal to the mean population. How would we go about this? Does anyone have a hunch? So effectively, we want all values that are above average. So packets already told us, right? So it would be without the names. In this case, the names actually doesn't have anything to do here, and be greater or equal to the mean of pop1, right? So we can index, and then now that we have a name vector, it will also have some auxiliary information and tells the countries that have that greater than average population are China and India. Here we have it, right? Now we can do things like this, right? So access all population values with less than max, but excludes the US. So in here, you can start seeing how we can start building more complex subsetting, right? So we can say, we want you to get the values that are smaller than the maximum, but yes, all the documents will be available. And these two, and the names are not USA. So this will return all the countries that are not the one with the highest population, nor the name is the USA. Now, again, something that I have spoken before is the idea of packages, and packages are collections of functions, data, code, and they extend the functionality of R, right? So you have base R, these basic functions, and then people use those functions to build a package that has worked those functions in to do something else. And then somebody else comes in and says like, well, with those new functions, I can create something else. And this has resulted in R being a very flexible and a very useful statistical programming language for data science. Now, there are packages for visualizing, for modeling, for importing data, et cetera, et cetera. And the way you can think about packages is similar to a program that you install in your machine. And the logic is that when you install the package, you just need to do it once. This is like downloading the software into your machine. And you just need to do the equivalent of double clicking and opening an icon because the package is already in your machine. So I know that in some programming languages, you have to download the package every time you're opening a session. In this programming language, you will install the package once and then just require it whenever you want to use it. Now, in a very similar fashion, keeping this analogy of downloading pieces of software to your machine, when there is a new version of a package, you will need to download it. Yes, we can take a little break, or like actually, let's just do an extra 5 minutes, and then we will take a break for 15, so that we can finish the packages. Okay, how does it work? There is a function for installing packages. The function is called install packages, and then you just type the name of your package within quotation marks. This is Sebastian's good practice recommendation. When you are running this function right here, install packages should always live in your console. Do not install packages on your R markdown scripts. Always do it in your console. So you're doing here install packages, name of the package, and then that should be living in your console, and then you just require the package in your code. When you're requiring the package, the requirement is with the library function, and then library does not need the quotation marks. You can require it by library quotation marks or without. Again, when you are working with this type of file, these are markdown files or Quarto documents, do not use install packages because your files won't compile. And this is the most common mistakes that happens to students who are taking the causal inference course, who are taking the intro to data science course, is that when they're doing their assignments, they install the packages at the start of the file, and then we receive emails at 11:59 p.m. Before the assignments are due, and it's like, hey, my assignment is not compiling. That's likely the reason. If you're doing this for your company or something too, and you're creating a report for your head of unit, again, like the file won't compile, you won't get to the end result if you have installed packages in this file, right? So avoid doing it like this. So we're gonna take a pause here. Let's pause for 15 minutes. So we're gonna come back at 11 and we can continue working on the script, okay? Hello, everyone. I see in the chat that some people are asking whether the session has ended. No, we're just having a 15-minute break, and we're going to start regrouping now. We're going to start in 1 minute. We're going to go back to what we were working on. Okay, so welcome back, everyone. And we're going to pick up where we left off. So we had been speaking about packages. Let's just regroup and just pick the main points from where we were talking about packages. Again, packages are collections of functions. You can think of them as pieces of software that you download into your machine, right? So the logic, this analogy extends to the logic of downloading and then just opening, right? You don't need to download the program that you're using every time you're using your machine, right? So you install the package once. My recommendation is that you do it in the console, right? Like this means to directly interact with R. This is where your install packages function should live. And then you just require the function in your code. There are ways to circumvent this. So there is a package for package management. It's called Pacman, and you will see it for those of you who are enrolling in the Masters of Data Science. You will start working with it also in the coming weeks. And those of you who are not, like I will send again, this is something also that came up in the chat while we were during the break. All the materials that we are working with right now, they are open. You will be able to access them both in my website and in the Data Science Summer School website. So under the R workshop, everything will be available to you. But also in my website, you will find materials for other workshops that talk about different things, such as package management and so on. Now, again, Sebastian's recommendation for those of you who are coming into the MDS and want to have peace of mind on your Sundays at 11:59 and enjoy Berlin, install packages in the console. Your assignments will compile without any issue. Okay, now let's work with some examples. So let's install this package. So all of us can go down here. I have already installed it, but let's do it together. So install packages with R. It will install the package, right? So it will download some version of the package that is in a repository online, right? And then it will tell me, yes, this has been downloaded, and now I have a local copy of that code that is effectively the package. Now what I can do is load the package. This is going to be the package readr. Readr is a package that is meant for reading foreign data formats, right? So what we will do now is use this package to load a CSV file. So what we're going to do is a little toy example of bringing everything together. We're going to load data from the outside. It's a CSV file that is hosted online. We're going to load it into a local machine. We're going to save it into an object that is going to be a data frame. And then we're going to perform some operations that we have learned in the last couple of minutes, right? So this is data about Pixar movies, right? The data set actually also lives in a package. So there are packages for everything. This is the Pixar Films package by Eric Long. And it compiles information from Wikipedia about Disney Pixar films. So it's a little nice toy data set. It has different data tables actually that then you can use to play with joins and so on. And then you can play with it on the basis of what we're doing, what we will be doing later. So of course, CSV files are very common. There are ways of working with CSV files directly with R, but you might know already by virtue of living in 2025 that when you go online, there are a million different data formats. And to make data readable to R, we have packages that can help us read effectively any data format that you can find digitally. So this package, readr, is a package to import tabular data. There are other libraries that can help us import data. So we have two of the most popular packages to import data are Haven and readr. So they include functions to import CSV files, DTA files. So this is Stata files, TSV files, SAP files from SPSS, etc. There are other packages that help us work with other non-tabular data. So there is JSON Lite to work with JSON files. You get the idea. If you like, the best way to approach this, and this talks back to one of the points that I made earlier, is that if you want to do something in R, you can just go on Google, or now if you want to also appeal to an AI assistant, how to load a data in X and such format. And the first entry on Google is going to be a Stack Overflow question that is going to tell you exactly how you can load it, what package you might use, 3 different ways to go about it, right? So this is how we're going to use this one. readr, 2 semicolons, read underscore CSV, and then the name of the file. You can use one accent, or you can use the 2 quotation marks. They are equivalent in this syntax. So like what we had before is the equivalent as doing this. So these 2 are equivalent. And then in here, we will have the Pixar Films object loaded. And this is how it looks like. It has the number of the film name as a character, the release date. So this is another data type that we have not seen in the past. This is a date. So R also knows how to load dates. It has the runtime, so how long was the movie, and the film rating, so this parental guidance, if it's PG or G or so on. We can also use the str function, right? So the structure function, and it will give us information about the data, right? So it is a table of dimensions 27 by 5, so it has 27 rows and 5 columns. It has these columns named number, film, release date, runtime, film rating, and then it has also some information about what type of data it has. So number is a double or a numeric variable, film is a character, release date is a date, runtime is a double, and then film rating is a character. If we're only interested in knowing the names of the columns, we can use the function names. It will print the names. And then we can also do a combination of things. So for instance, we have that runtime might be a little bit ambiguous, so we can change the name of that. So in the 4th position, we have a name for that, is runtime. We want it to be film duration, right? So this is equivalent to something that we have done. And now Pixar Films has, instead of runtimes, it has film duration. We can apply different other functions to data sets, something like summary. Summary will give you a summary of the data set, as the function suggests. So if you have numbers, it will tell you some, like, you can really see that this is a programming language that was made by statisticians. So it will give you some measures of spread, the quartiles, the minimum value, median, mean. If you have characters, it would give you, it would tell you, well, this is a character, and then the mode is a character. So like you can really see that this is the underlying logic of this being a statistical programming language at the core. You have functions like the number of rows, number of columns, the dimensions. You can start playing with this. Now, We have done base R indexing on vectors. And now what we're going to take a look is at indexing with data frames, right? So this is not just the single, like this unidimensional array, but now we have multiple dimensions. As you see, we have the columns and the rows, right? So when we have this two-dimensional indexing, the logic is the same, is the square brackets, and then you're going to have, in the first place, you're going to index the row, comma, and in the second place is going to be the column. So let's take a look at this. This is going to index the first row. If we were to have this, it will return the first column. If we were to have this, it will return the first row and the first column. So again, the indexing in this two-dimensional space is row, column, right? And you can leave empty either one if you want to keep it, if you want to just index one or the other, right? You don't have to specify everything else. Now, you can use the concatenate function in the same way that we did with the unidimensional. So say you want to get the first and second rows, right? You can use this as well. And you can also access rows, for instance, with other functions. Like in this case, we're getting every value from 1 to 5. It will return the first 5 rows. Now, we already did this, right? So how would we access the first row and the first column? So it would be Pixar films, first row, first column. And this will return the first row, first column. Say, for instance, we go out of bounds and we say we want to return the value on the 29th row that doesn't exist. It will tell us it is an NA, and we will talk a little bit about NAs in R in a second. So a value that does not exist. Okay. So does anyone have a hunch on how we can access the element of the Pixar films stored in column 3 and row 10? Exactly. So Pixar films, again, like this was to throw you off a little bit with the column and row, right? So the logic like of this exercise was so that we remember that the first value needs to be the row and then the column. So like everyone in the chat is getting it correct, right? Now, there is another way of indexing, and it's the dollar operator. And in this case, the dollar operator is used to specify a variable within a data frame. So instead of indexing with the square brackets, we can use the dollar operator and we type the name of the data frame. And this is opening up the object itself. So if we put one of the column names, it will return the whole vector of film duration, right? So when we use head, it will give us the first 6 values. So this operator is doing the indexing. This would be the equivalent of doing film duration is 4. So this would be the equivalent of doing Pixar films 4, right? Though it is already returning just the vector. Now, you have the table function, and the table function, what it does is that it creates a cross tabulation. So I can create a cross tabulation or just tabulate one variable. These are generally variables that are of non-numeric variables, and it would return counts of how many values of those things you have. So we can take a look at the film ratings, right? So we have the different parental guidance ratings in our data. And say we want to know how many of each we have, right? So we can have something being G. So 13 movies of Pixar are 13. There are 14. There are 3 that are NAs, 1 that has not been rated, and 10 that are PG, right? A lot of what we do in R is counting, And as data scientists, a lot of what we do is actually just doing counting and fancy averages when we do modeling. So like tabling is very important. There is another package, it's called Janitor, and it has a function called tabil. And that's an extension of this function that works very well with what we will learn in a couple of minutes in the tidyverse. Okay, so again, how would we access all the elements without film? Without the $sign operator, we can use the indexing by number, or we can do the indexing by name. This is totally fine. Say we wanted to extract the oldest field using the $sign operator, we can do something like getting the minimum release date, right? And then it would tell us, well, the minimum release date was in 1995, in November 1995. That should be Toy Story, right? So it's a movie that is now 30 years old. What is the, like, you can also index using that same logic, index and extract all that information using that logic. So you can start concatenating this sequence of functions where you know what you want. So you want the one that has the minimum, like the lowest or the earliest date, and you want to extract that pixel release date is that minimum value and just index it, and you would get this. Now, take a look at that bit of code that you're looking right there and see how complex it looks, how messy it looks. And in about 15 minutes, when we move into the tidyverse, we're going to see a way in which we can achieve the same results with something that mimics the way we speak natural language, right? The way we think about problems. And that's the beauty of art. Like, something that makes art very powerful is that, yes, we can do things in a logical manner that mimics other programming languages, but the extensions that have been created also mimic the thinking process of a data scientist that thinks about a problem, knows what output they're expecting, and then follows a sequence of steps. Okay, now NAs in R. R has a little value, another data type. It's this NA, and it denotes a missing value. So we can create this vector with a missing value, and what we will have right here is this vector that has an NA. Now, there are some functions, especially when you think about statistics, that will not work when you have NAs. So when you try to take the mean or the sum of values that have NAs, they won't work. And that is because the people writing the programming language want you to be very explicit about the computations that you're doing, right? They want you to know, okay, you want me to get an arithmetic mean, but you have missingness. Is that missingness may be informative? You should be very explicit about what you're trying to estimate. And as such, like, many of these functions have an argument that will let them know, okay, I am aware as a data analyst that there is some missingness, and I just want you to get rid of it and still give me the mean. So, like, for instance, in this case, NA remove true will give you the mean of the vector vec without NAs. So it would grab the four values that have numbers 4, 1, 2, and 3 and get rid of the NA. And then the sum will do the same, right? You can add new observations. So say we have a new data frame, this new row that has a new film that was not into the data. You can use another function called rbind, and it would bind on the row basis. You can also cbind to bind on the column basis. So in this case, we have this new data frame. It has inside out, the release date, and so on. We can then use rbind to add it to our new film. And then now it would be a data frame of 28 by 5. You can add new variables, so create new variables. So say you have the film duration in minutes and you want to turn it into hours, you can grab the duration in minutes and divide it by 60. And then with the $operator sign, say, I want this new column that is going to be film duration hours, and it's going to be this value right here. And now our new data set is going to have the film duration in hours. right? So again, this is starting to become a bit more flexible. In R, and this is something that will happen, a lot to us, is that we will encounter errors in R, right? Now, there are errors that will prevent the code from running, and then there are errors that will run. We will get a warning, and the code will still work, right? Those that will stop the program from running, those are easy to spot, but sometimes there are errors that will give you a warning and you won't notice what happened, right? So in this case, for instance, vector error, say we want to have this right here. This will run and it will give you a warning, NA is introduced by coercion. And then in here, the vector error vector will be created, but you don't know what happened. So in this case, we as people who speak English, we understand that this is a representation of a number. This is a representation of a number. And in principle, this is a representation of a number, right? But R doesn't know how to turn this string 3 into a number. So it will turn it into an NA. Now the code will run. And this is, of course, an example that is very in your face, so you will be okay, yeah, this makes sense. But sometimes you will run code, you will get results of your analysis, and maybe these things might be happening in the background. This is a point that I want to make, and it's when you get warning messages, pay attention to them. Like we at the Heritage School, we work in data analysis and data science for the public good. We work in policy environments. We work in trying to improve the welfare of people. And if you make mistakes when you're analyzing data and then create insights from those data and try to leverage those insights for policy and so on, maybe having these types of errors that are programming errors that you could have spotted if you were to look at what's happening when you're running the code, then maybe you can avoid misusing data, for instance, or getting results that are not reflective of what's true. Now, there is another convention, and it's the double colon operator. You might have seen it when we worked with Haven, and it's this double colon, right? You can write the function if you do library Haven, or if you do library read R, you can just run the function without this. But what I want to encourage you to do already from the starting point is to use this operator, and the convention is you write the name of the package, a double colon, and then the name of the function. Why do we do this, and why is it important? This is the case in other programming languages. It's not necessary in R, but when you load a package, sometimes people name their functions the same, right? So for instance, when you load the tidyverse, you will see that there is a function from the Dplyr filter, and it masks over filter from the stats package. You have a lag function that masks over the other one. This convention of the double colon thing is to make collaboration easier, right? That you ensure that you specify that the code everywhere that is being run, that the code is specifying what function from which package you're using, and that way collaboration can be easier. Because say you're running code in your machine and your collaborator is running code in their machine, and for some reason they're using filter from the stats package and you're using Dplyr from the filter from the Dplyr package, and when you run the code, this might result in totally different output. So this is just an invitation to use the double colon operator from the start. Again, function, double colon, package, double colon function. In here, we have some best practices for you to take a look later. So how to structure your scripts, how to name things, working with directory and projects, setting your working directory, all those type of things that are more miscellaneous. You can read them in the HTML file. Now, again, for actually learning R, the key to learning R is to practice, make mistakes, and Google. And by Google, I use Google as a shorthand of seeking answers to those mistakes in repositories of answers provided by the R community. The R community, this is an open source piece of software, and the R community is super active. There are many people willing and willing to share, willing to provide tutorials, and willing to help solve issues. There are Discord channels, there are Slack channels, there are forums. There are different means in which you can engage with this community and ask your questions as you're learning. Okay, now we're gonna move to the cool part, and this is like, so we have done the base R foundations. Now we're gonna move to the why R can be. Yes, we will share some links to our community, Discord channels, Slack channels, and so on. This suite of packages, the tidyverse, is why I think for us as applied data scientists in companies, in government, in science, so I am a computational social scientist, for instance. Yes, I do care that my code is efficient, that it runs smoothly, that it's not occupying so much memory, but I also care about creating insights so that I can find those, again, like, sorry for the tautology, get to those scientific findings that then I can use to inform policy, to inform the scientific base, and so on, right? The tidyverse. We will leave the base R solutions behind, and we will make our lives easier. So you can remember about like 15 minutes ago when we saw that line of code that was, I don't know, function within a function within a function within a logical operation within a function. We can get rid of that, and we can think about the tidyverse. So a lot of people are not keen in introducing the tidyverse from the very start. I am a contrarian to this, and I think that there are many people who are actually more and more keen in the idea that it's okay to learn also at the start by working with the tidyverse. And the logic is relatively simple. The tidyverse has outstanding documentation. It has big community support. It is a collection of packages, yes, but it's also a consistent philosophy of data analysis and a consistent syntax. And this syntax mimics the way we as plain data scientists think about data problems. It's convenient, it's easy to map data problems into natural language. I want to grab this data frame and I want to subset it in this way, then I want to arrange it in this way, then I want to follow this logical set of steps. Okay, so you can read about the tidyverse, but what we're going to do today is take a look. Exactly, it codes tidy. What we're going to do is look at a couple of packages from this tidy syntax, right? Base R, extremely useful. I use it a lot. Sometimes the more efficient and the quickest answer to the data problem that you want to solve is base R. So why not just use that one-liner instead of writing 20 lines? But just for the more complex tasks, sequential tasks, the tidyverse is just more intuitive. So what we're going to do in this part of the workshop is understand tidy data, which is going to be 10 seconds because we all intuitively know what tidy data are, because tidy data are just your vanilla tabular data format, but that's the data format that is and the underlying principle of the tidyverse. Then we're going to identify the purpose of some Dplyr verbs. Dplyr is a package for data manipulation. So we're going to see 6 verbs, 6 functions from this package so that you get an idea of, so I don't have to complicate my life as I was doing in the past half an hour, and I can just do this. Then we're going to restructure some data sets with tidyr. Tidyr is another package from the tidyverse that helps you reshape your data frames, so like transposing them, doing this type of operations. We're going to get into the basics of data visualization with ggplot, and this is one of the packages that makes our very superior programming language when it comes to communication. In fact, many other programming languages grab this grammar of graphics and try to build wrappers around the ggplot because it's just very flexible, and it's very intuitive to build graphics. And then if we have some time, we're going to learn a little bit about functions and iteration with Perl. I don't think we're going to get to this, but you have all the materials, you have the exercises, and you can work with this. And then that part is the part where we get into the nitty-gritty of, okay, I have a base of understanding how to work with R. I have data tasks. How do I abide to this DRY notion? So don't repeat yourself, because if you repeat yourself when you're programming, you're prone to make mistakes. So how do I make things in a more concise, sort of self-contained environment where I just need to change some arguments and the code will iterate over multiple operations that I have to do to avoid mistakes by copying and pasting or doing those things. So the tidyverse, well, the tidyverse is a collection of packages, right? They have an underlying design, they have a syntax, they have a structure that is making all these packages that are created by different developers or teams of developers, rather. They all share this structure. At the highest level, it is a language for solving data science problems, right? So this is a language for solving challenges with our code. And the primary goal, the logic under this is, how do we create a syntax, a way of communicating with the programming language that makes the conversation between the data scientist, the data analyst, the person working in the ministry that is doing the data analysis with the machine in a way that is intuitive, right? So this is like the underlying philosophy is to simplify data tasks that, of course, programming languages are written by programmers, and programmers have been trained classically as programmers, and the tidyverse is trying to bridge this distinction, this gap between people who are classically trained programmers into the more general data science enthusiast user. The beauty of this is also that if you learn one package, then it is super easy to learn the next because they share the syntax. So at the basis of the tidyverse is tidy data. And you all know tidy data because it's just tabular data. We have spoken about it already in the past, but tidy data is this tidy format. It's this mapping structure where you have a variable that forms a column, an observation that forms a row, and then the junction of those are the values that correspond to that observation and that variable. So in this case, I don't know if it's visible to you. In here we have a country, and it's going to be Afghanistan. And then in here we have a year. So this is going to be Afghanistan in 1999. That's tidy data. Those were the 30 seconds that we should invest in thinking about what the underlying data structure for the tidyverse is. Now, the tidyverse, so like you can load the library. If you don't have it, then you would go install packages. Again, Sebastian convention, install packages always in the console. Install packages, quotation marks, tidyverse, press enter, and it will download all the packages in the tidyverse. And when we load the tidyverse, we load the suite, right? So we load a whole bunch of those packages. So it will load ggplot, table, dplyr, tidyr, all these packages there. Some packages that are part of the tidyverse won't be loaded automatically, but you can just call them on your own. These are the packages that are part of the tidyverse. So you have things like Broom. So Broom is a package that helps you extract model output. You have Haven, we spoke about it, for extracting, for loading data formats that are foreign. You have JSON-like to work with JSON data. Dplyr, it's to work with databases. You have rvest for data web scraping, Stringer and Stringy for working with strings, so like doing regular expressions. You have lubridate to work with dates, ggplot by far the best package in R, in my opinion. So to create beautiful visualizations, to communicate insights, you will see that a lot of the things that we do as data scientists is or like the two core things are cleaning data, making sure that data are in shape, and then figuring out how to communicate efficiently the insights that we have gathered from this data to people that have 1 minute of attention. And then in that space, this package is very useful. You have a whole bunch of packages. You can take a look at the tidyverse in online. So if we go here, you will see that all the packages of the tidyverse have their own website. And this is how generally the packages look like. So say, for instance, we want to look at Dplyr. This is the documentation that all packages in R tend to have. So this is when you write a package, of those of you who are doing the Masters in Data Science, you will see when you write a package, if you document it while you're writing it, you can create these documents automatically with a package. And then in here, you have all the documentation. It will tell you, okay, this is what we do. We have these functions. You can also see a little bit of how to get started with the package. It will have some exercises that you can see how different functions are working. You can have articles speaking about different functions. You can even see, for instance, in here, okay, why Dplyr versus base R? So like, how can you use Dplyr and how does it compare to base R, right? So you can start to see that the functions in Dplyr look a lot like plain English. Like this is effectively how we speak. Rename something instead of saying, oh, grab those names, and those names, if they equal something, name them something, right? Like it's not intuitive. In here, we're telling it, grab the data frame and rename Y with X, right? It's very, the logic, the syntax is very similar to the way we as data scientists and as humans relate to solving problems, right? So all these packages have these general landing pages. So if you Google a package, you will find the documentation, and you will have these introductions. You also have cheat sheets, and then you can look at the different articles on like, how do I play with ggplot, how do I extend it, etc. Okay, so this is what we have for the tidyverse. Now, say, for instance, you all in the MDS, well, you will use in a couple of weeks from now, so in about 3 months, you will be using RVest to do web scraping, or you will use StringR to work with regular expressions and extract information from those websites that you have scraped to create your own databases. And you will also use a package from the tidyverse to engage with that database that you have created. So there is a package pretty much for everything. So what we're going to do now is the first part of the workshop, or this tidyverse primer, and it's going to be data manipulation with Dplyr. We're going to learn 6 verbs. These are 6 functions that are part of the Dplyr package. And we're going to work with some data sets, some toy data sets, so that we can perform those functions and see how this is mapping onto natural language. So the first one is going to be Dplyr select. And this is the equivalent of what we were doing with column-based indexing. So this is a function that we will use to keep or exclude some columns. Then we have Dplyr filter. This is a function for row-based indexing. So this is keeping rows that satisfy some conditions. So I want to subset my data for only countries that are low income. This is what you would use. You have mutate, and mutate is a function that helps you add columns from existing data or edit existing columns. You have group by. It lets you cluster within your data frame, and it generally comes used in junction with summarize. So you group by and get a summary. So it gets you summary statistics from those groups. And then we're going to work with arrange, which is, as the name suggests, as many of these have very self-explanatory names, it will reorder right? It will arrange rows according to some arguments that you give it. So let's get to work. We're going to work with one of the most commonly used toy data sets in the tidyverse. This is the penguins data set. It's a data set that has information about sightings and recording of penguins in the Antarctica. For those of you who are not familiar with penguins in the Antarctica, there are these three types. There is Alison Hortz, who is a person part of this art community, and she does illustrations for learning how to code with R. So she made this very beautiful illustration of the data set. And the package, it's called Palmer Penguins. You can, again, download the package here. So it would be only one, install packages, Palmer Penguins. It will download the package, and then the package contains the data set. So you can run this library. Now, we will use this data set to demonstrate and practice a little bit how these functions work. So this is penguins observed in Antarctica, and it has eight data points of information about them. So it has the species of the penguin, so one of those three that we saw, the island in the Antarctica where that penguin was observed, the length of their beak and the depth of their beak, right? The length of their flipper in millimeters, how much they weighed in grams, the sex of the penguin, and this is a project. This was a scientific project, so this is data from a scientific project, a group that did expeditions in the Antarctica. So they went over a span of 3 years, and it has the year where the particular penguin was observed, right? So this is how the data set looks like. It has the name of the species, it has the island where it was observed, what the length of their bill is, what the depth of their bill is, the length of their flipper, and their body mass, sex, and the year it was observed. Now, the first verb that we're going to meet again is select. Select is the equivalent of what we were doing before with column-based indexing, right? So again, select for column-based indexing. And this is a case where we would like to keep only some columns. Say you download a very large data set with many columns, and you just want to use 3 of those columns for the analysis. So you select and say, I want you to subset this data set to keep those 3 columns, right? The way you would do this is with the names of the columns, right? So in this case, we have species, island, bill length, and so on. And the syntax of all these functions in the Dplyr universe tends to be relatively similar. The first input can be or will be the data. So in this case, it will be Dplyr select. What data frame do you want me to perform this operation on? And then the second column, the second argument would be the argument specific to that function. In this case, the columns. So for instance, the following chunk will select from the penguins data set 3 columns: species, island, and year, right? And then the result would be that instead of getting the data frame that has 8 columns, we will get the data set that has these 3 columns. Okay, so everyone is there with me? Now let's do a little activity together and think about what should we do is that if that in addition to these 3 columns, we wanted to get the body mass and the sex as well. What can we do to get those columns in? So again, like what we can do is ask for the body mass in grams and then the sex. And in this case, then it would keep those, right? So again, you can specify the data set and then you can tell it what other variables do you want to keep. So in here we have that one, right? Here is the solution of that. But you remember the negative indexing? So in here, we can do that, right? Like say we want to keep 5, but we can also do something that is negative indexing. Say you have a data set that has 20 columns where it's going to be very time consuming to type 20 columns if you want to delete one. What you can do is the negative indexing and telling it select everything but the sex, for instance. Right? You can also tell it select everything but sex and species, and it will do this, right? So again, select is a function from Dplyr. It does column-based indexing, and it does indexing positively. So specifically, you give the numbers of the columns, so like the locations of the columns or the names of the columns, or you can do negative indexing and you can do the minus sign, and then you can tell it, I want you to keep everything bad. So that's the first verb that we have seen. Again, we will go over a little bit of this. Okay, so the concern of the colon, the double colon operator, is because sometimes functions might be named the same in other packages, and what we want to make sure, like in the cases that we're using, this is not so much, but for instance, with some of my collaborators, we might be using packages to do statistical modeling. There is one particular package for statistical models to run mixed effects models that has a function that is called select. Normally, the 99% of people who are using a function called select in R will totally be using the Dplyr select. But if you load the other package after loading library, the select from that package is going to mask over the select of the Dplyr. And then when you're running your code, if you only have select and not Dplyr select, the behavior will be that one of the function of the statistical modeling package. What this means is that your code will not run the way you expected. When you're running your code for your own or for your assignments or for your project that you're doing a little data science exercise on your own, this is likely not a problem because you know what's happening. My hope and my expectation is that many of you will move forward this data science path, and in a couple of years, why not, you'll become, not even in a couple of months, within the next year, you become very good data scientists that are working on collaborative teams, right? And then at that point, managing packages, managing functions, maybe even delivering a product, right? This might require you to have a package management that is very self-contained and try to avoid those errors. And that's why today, in the first day, this is something that most people don't do, but this is why I ask you to just use this convention, right? Let's just use this convention and try to use it as a best practice already from the start. In this case, again, like this is something that at least pointed, well, like actually, like this will work just fine, right? If I do select penguins, comma, sex, like this will run like this. So just so that everyone notices, yes, it will run like this. If your collaborator for some reason has a different environment in which they're working and they for some reason loaded a package afterwards and it corrupts the thing, then it's going to make collaboration difficult, or it's going to make at least more coordination, increased coordination costs between you and them, because then you're going to have to tell them, oh no, maybe you're having this error. So that's what we're doing. Coming back to the tidyverse, coming back to Dplyr, coming back to the verse that we're meeting. So we have met the first one, select column-based indexing. The second verb that we're going to meet, the second function, is filter, right? And this function uses logical tests. So these very first things that we met in the workshop, and they do it to filter, to extract specific rows that meet those statements in the data frame. So what will happen is that filter will pass through the data frame and will ask itself a question. This data frame, let's grab the rows that meet those requirements. So you can use some logical operators. We spoke about them: equal to, not equal to, greater, smaller than, or less than, and, or, in, and then it will return whatever is there. So let's think about this. The syntax is very similar again to select. So in this case, it's Dplyr filter. We have the data set penguins. And when we look at the data set penguins, penguins has years here. So if we look at the penguins data set here on a second, you will see that there are year 2007, but there's also 2008 and 2009. Maybe we can take a look at maybe the last page. If we go in here, the years, it's not visible here, but these are things from 2009. What we can do is tell it, just keep the penguins from this year. So when year equals 2007, it will give you those 110 penguins that are from 2007. So these are penguins. If you take a look at that data frame, it's 344 rows, so 344 observations of penguins. If we were to look at the ones in 2008, it will give you the 100, it will return the 114 penguins that were observed that year. So we have this code, right? The penguins from 2007. Now let's try to do this exercise together, where in addition to keeping all the penguins from 2007, we want to keep the penguins that have a species called chinstrap. How would we do that? So we want to keep penguins from 2007 and species that is equal to chinstrap. Yeah, so Andre just sent us the answer, and it would be using this other logical operation, right? I want you to keep everything from 2007, and also they need to meet this other thing, a species equals to, remember that the equals needs to be twice equal sign, chinstrap. And then in this case, it's going to return, if you see, only the 26 chinstrap penguins that were observed in 2007, right? So if you try to even think about, okay, how would I go about doing this in base R? Things start to get complicated. It's still doable. We would have the logical operation and we can do it. But as you start having more and more things on top, it gets complicated, right? So in here is how we would do the chinstrap exercise. Now, this is what, to me, makes R a very powerful language. Other languages have this type of forward operation, but not many do. And this pipe operator is what makes R very intuitive and very useful for data science as people who are going to be establishing these data science workflows. So the pipe, you see it right here, is a percent, then the sign, and then the percent comes from the markdown package. And every time that you load a package from the tidyverse, they load this pipe automatically. So you don't usually load it, but if you want to get other pipes that have different functionalities, you can do it, and they come from the markdown package, right? Now, these will be some of your best friends in R. And what happens here is that pipes are a very powerful tool for clearly expressing a sequence of operations. So this is my low-tech pitch for why pipes matter. So say I want to bake a banana bread. There are multiple ways in which you can go about programming, right? There is an object-oriented version where you would have a vector of ingredients, right? This will be ingredients, right? This is a recipe. You can do it without the eggs and add canola oil maybe. And then you have, for the banana bread, you will have flour, sugar, eggs, butter, baking soda, and then you will create objects, right? So when you're making the banana bread, maybe you will have a function that it's called mash, and inside the mash function, you will put the bananas. And when you mash the bananas, well, you will get an object that's called mash bananas. In programming language here, what we would be doing is we mash the bananas, we save them into an object that is going to go into memory, and it's going to be the mashed bananas is going to be an abstraction, right? Then what you're going to do is grab those mashed bananas from memory and mix those mashed bananas with these ingredients, right? So it has mix, whatever is here is going to be the mashed bananas, and then the second argument is going to be the ingredients. And when you mix those things, you're going to end up with the batter, right? Once you have the batter, maybe you can place that batter, right? So you use the place function, you place that batter in a tool. In this case, the tool is going to be a baking pan, and that's going to result in the sheet. The sheet is going to be another abstraction that goes into memory, and you will then need to call. In a final step, you're going to bake the sheet in an appliance. The appliance can be an air fryer, an oven, whatever it is. In this case, it's going to be an oven, and it's going to be at some temperature for some time in minutes. And then voila, you have your banana bread. This part right here is still not so complicated. We're going to see in a second what is also another way, which is very nested in functions. So a function within a function within a function within a function. This way it's still readable, right? Like we create abstractions, it's going to load onto memory, and maybe it's error prone. So this is still okay, but it's time consuming if something changes here. Maybe you don't know what's changing down the line. Instead, this is where pipes come in. You grab the bananas and you pipe them down so they go forward, and then they're mashed. You don't need to create the mashed bananas object, because in here, the idea of the mashed bananas already exists, and then they just move forward to the next function, right? So instead of creating the mashed bananas and passing them down, things just go in a flow, in a logical flow of steps that you as a data scientist, as a data analyst, know that you need to perform to get to the end result of your data analysis pipeline, which ultimately is, I want to have a banana bread. So you have the bananas, you mash them. The mashed bananas exist abstractly. They're an idea, they exist, and they just get passed down. If you want to get the banana bread, you don't care about the mashed bananas at that point, right? You pass them, you mix the ingredients. In here, the batter still exists, but you don't have to create that object. You can place the batter inside the baking pan and you can bake it. And at the end, you have the banana bread. So this idea was introduced in the tidyverse and in this logic, and it was so powerful that the core R development team said, this is incredible, and they developed a native pipe for the base R. So now base R, when you download it, since the 4.1 version, it has its own pipe. So we will focus on the Magritte R version of the pipe, right? The one that is native to the tidyverse, but the logic is very similar. There are some things that are different, and you can read a little bit more here in this blog by the people from the tidyverse that explain a little bit what are the difference between the two. So in here, we're going to see some code. It's going to be code written in ways that work. They work, they're totally fine, but they're less than idea for us as data scientists to understand what's happening inside the code. One of them is going to be object-oriented, which is something like this. Again, you create objects. And the second one is, so that one is repetitive. The second one is nested. So it's only one, but it's hard to read and debug. So in here, we want to end up with a data frame. This is our task. We want to end up with a data frame that has only chinstrap penguins that are observed in the 2009 year, and we want to keep only 3 columns: species, sex, and year. So we first filter, like we have the penguins data set, we filter, keep only the 2009, and this is, okay, now I have only the 2009s. Then I do the same, but keeping only the species chinstrap, and now I have all the 2009 chinstraps. Then I want all the species, sex, and year, and I have only 2009 chinstraps, which is this and this. And then I want to keep species, sex, and year, and then I save that into a final data frame. This is still okay, but there are many steps that can be compressed into one. Now, This is the same code into one. This is how programmers generally program. And in many programming languages, this is what you would do if you wanted to do that. So instead of saving everything into one object and then using those objects, you would run a function within a function within a function. I don't know about you, but this is totally unreadable. If you mess up one parenthesis, then the whole code collapses. And if you have, like, this will be generally something that you will encounter as you start moving forward. You're typing fast when you're programming, you have your headphones, you're at a cafe, you make an error, you put a comma, you don't put a comma. Debugging is something that we do a lot. How do you debug something like this or even larger, right? So this is where the pipes come in, right? And maybe we can keep this instead of trying to come up with the answer together, we can look at how we can do it, right? So the pipe is very powerful, right? So instead of doing this, so this nested function or this object bit, we can just think about what the data problem at hand is. Sebastian, as a data analyst, wants to work and do the analysis of the data, manipulate or transform this data so that he only works with data from the 2009 Chinstrand penguins, and he only cares about these three columns, right? So those are the things that I care about. How do I go about this? Well, I'm going to grab the data frame. I'm going to filter. So I just want the rows that fulfill those requirements, year and species, right? And then I'm going to select the columns that I care about, right? So it grabs this. It doesn't need to create these other abstractions, but it grabs this and it runs sequentially. So if I were to only run these two lines, it will return the Chinstrap penguins from 2009, and then it will grab whatever is created there, pass it down the pipeline, and select from that the three columns. Does everyone see this? I hope that you appreciate how this is, of course, perhaps easier than doing this. Now, this is still a short data processing pipeline. Sometimes things get very complicated because you need to do a lot of data transformation, right? So this sort of flow of operations that you want to perform in your data is I think, something very powerful for us. Now, so we have seen two verbs. We're going to go to the third verb, and it's going to be Dplyr mutate. And mutate lets us create and modify columns. And then the most common use case for now will be to create variables based on existing ones, right? So say you have this penguins data set, you're working with a US American client, and they're more comfortable working with the weight in pounds rather than in grams. So the syntax for mutate is you have the new variable name that you want to create, one equal sign, and then whatever conditions, whatever arguments you want to create. So for instance, in this case, we have the penguins data set, right? We have the body mass in grams, and we want to tell it, okay, now I want to create a new column that is going to be body mass in pounds, and that's going to be equal to the body mass in grams divided by this constant that is going to be then the transformation of grams into pounds. When we run this, the last column that is going to be created is going to be body mass in pounds, and it's going to tell us the body mass in pounds, right? So you can then share this value or do the analysis then for your US American client, right? So instead of saying, okay, this is 3,750 grams, it is 8.3 pounds, right? So everyone is there with us. So we have the select command for column-based indexing. Effectively, I want to just keep these three columns. I want to keep those, or I want to keep everything but that one. Then there is filter, row-based indexing. Then there is mutate to create or modify columns. Now, let's do something. How can we edit this to add a new variable that is called body mass in kilograms? So what can we do to create the body mass in kilograms? So maybe we can do this. body mass in kilograms. Exactly. So Dora just told us, gave us the answer. We would, instead of doing that, we could do divide by 1000. And then that would be, then in here, we would have the body mass in kilograms, right? Now, when you're doing mutate, you can do something like run multiple calls, so you can create multiple variables in one go. So you can create body mass in kilograms and body mass in pounds in just one function call, and it runs everything sequentially. So now you have body mass in kilograms and body mass in pounds. And then something else that you can do is that since this is reading sequentially, you can do something like grab in here, for instance, at this point, when it is reading sequentially, it would create the body mass kilograms. You can also use the body mass kilograms and then just divide by the constant for the kilograms, and then it will run it. So in this case, R is like the way it would work is that it will run things sequentially. So first we'll create body mass, and you can use what you have created before to use it following. Something that will also happen is that you, for instance, if you do something like this, or override, we have created body mass kilograms, then body mass in pounds, then body mass in kilograms again. It will write over it, and then it will take the last thing that you did, right? So it runs sequentially, and now this will take that value right there. So that's how you would work with mutate. Again, select for column-based indexing, filter for row-based indexing, mutate for creating new new columns or editing values. Now, this is the junction of group by and summarize, and these two verbs generally come together. So when combined, summarize will create a new data frame. So it will have one or more rows in the combination of grouping variables. If there are no grouping variables, then the output will be just a single row summarizing all observations in the input. So say, for example, we have the penguins, and we want to get the heaviest penguin. So we can do something like summarize the heaviest penguin, and the heaviest penguin is going to be the penguin with the maximum body mass. And if we run this, it would tell us, oh, the heaviest penguin is 6,300 grams, so 6.3 kilo. It's a heavy penguin. Now, when you use that summarize in junction with group by, right? So you would do penguins, group by, and summarize. It would cluster on this grouping. So it would give you then the heaviest penguin for each one of the species, right? So it would tell you, oh, for Adderley penguins, this is the heaviest penguin. For the Chinstrand penguin, this is the heaviest penguin. And for the Gento penguin, this is the heaviest penguin. Now, if you notice here, we're also adding this argument that is that groups drop. This is not going to be very salient for you right now in the workshop, but when you're working with this data, and as you pass down this data, you continue working on the pipeline and so on, the grouping structure, if you don't ungroup, carries downward, right? So we just recommend when you're done with the clustered analysis of like, okay, now I don't need to have things clustered by species, you just use either the ungroup function or the groups drop. And I know this is slightly cryptic right now that I'm mentioning it. I just wanted to put the nugget there so that when you're working, oh yeah, I remember Sebastian mentioned something, and there is someone that is one of the best R community persons in the whole wide world. He's a professor, so his name is Andrew Hayes. He's a professor, I believe, in Utah, and he has the most beautiful art tutorials. Right in here, he's having these tutorials. You can all access them, And he has courses about data visualization that he teaches at his home institution. He has courses about causal inference. So even those of you who will be taking the causal inference course, you can take a look at his courses. His materials are excellent. And in here, he has a little bit of more elaboration of what happens when you have leftover groupings and non-groupings. And you can see all of the stuff that he has created. Very cool materials. He has a blog also where he talks about how to use different R-specific things. Very useful tools that he creates. Okay, so now you have the nugget. There is something about group by that I need to remember. So let's see what happens. Okay, so we have this. Let's do an exercise all together, and maybe you can tell me what do you think will happen. Okay, so you do the lightest penguin instead of the heaviest penguin, lightest penguin, and then instead of max is going to be min. And then this is going to give us the lightest penguin. Now, what do you think is going to happen if, in addition to species, we get year in this mix? So it is going to grab every single combination of these values, and it's going to tell you the lightest penguin in 2007 was this way, the lightest penguin in 2008 was this way, the lightest Adelaide penguin in 2009 was this way, right? So then you can start playing with these groupings and create clusters that will give you information about your data. This is super useful also when you're trying to get a sense of, okay, I received data from the sales team. Let's get an idea of what is there, like just explore data, getting a sense of what's in your data. Okay, so this is what would happen there. Now, the last verb that we're going to see is arrange, and the verb is pretty self-explanatory. It arranges, right? So it orders the rows in the data frame by the values of the selected columns, by default in ascending order, right? You can use another argument that's called descending if you want to arrange it in descending order, right? So you can do, for instance, in here, arrange by the length of the bill, and now you have the length of the bill in ascending order from smaller to higher. If you do descending order, it will go then from higher to lower. And now it will be the highest value to the lowest. If you do this, the arranging on characters, it will be descending order would be from the ordering of the alphabet. So it would grab the values with A to Z. And if you use the descending command, it will go from Z to A, right? So it can also work with, I don't know, species. So if we go on species here, it will render it again to the chin strap and then the Adelaide penguins. And if we were to do it without the descending for helper function, it will go Adelaide to Gentoo. Okay, perfect. So maybe we can do this later, or we can just take a look at it. Our challenge is to create a data frame arranged by the body mass of the penguins observed only in the dream island, right? So the data problem is we want to end up with a data set that contains only penguins observed in the island in the Antarctica called Dream. And then we want to arrange it from the heaviest penguin to the lowest to the lightest penguin, right? So we would grab our data set and we would ask we would then break this problem down into multiple steps. The first step would be, okay, I want to arrange only on the basis of this particular subset of penguins, which is those that fulfill the logical operation. They come from they were observed in the island Dream. So this is this 124 penguins. And then I want to see what was the heaviest penguin. And then in here we have that the heaviest penguin was this chin strap penguin. It was roughly 4.8 kilograms. It was a male penguin. It was slightly large, right? So that's how we would do it. So a couple of questions now that we have seen these 6 verbs, right? So the first one is, which of these 4 functions would we use if we want to do column based indexing. So effectively, I want to select these columns, or I want to select these columns, but this one. Which of those four functions? That's column-based indexing. Exactly. Everyone in the chat just typed select. So select, again, is column-based indexing. So that makes the second question easier. Which function does row-based indexing? Excellent. Everyone is saying filter, right? So select column-based indexing, filter row-based indexing, two ways of subsetting our data, right? Now, how long was the observed bill of the longest observed bill of a gentle penguin in 2008? Maybe we can come with this one together. So we want to grab the penguins data set, and what we want to know is we want to get to penguins in 2008, and we want to extract the value of the longest observed bill. So maybe we can grab some inspiration from here. Something like this. There are multiple ways that we can go about this. And we can grab some inspiration from here. Maybe I'll give you 30 seconds to think about what we need to do, what we can adapt, and so on. So again, we want to only work with Gentoo penguins observed in 2009. So we can do in here species equals Gentoo and year equals 2008. Then we want to do bill length in millimeters. This is the low-tech version of this. And then we would see, okay, that one had a length of 54. Something else, and there are many functions you can Google. You can use GPT, Gemini, DeepSeek, AI agents to also help you in trying to think through problems. How can I approach it, right? And you can do something like this. For instance, there is another function that is called pool, and this one will return the actual scalar. So it will return the value itself, and then in here, we want to get which one is the maximum build length. Pool, oh no. This one didn't work because actually it's not with pool, is then we would do max build length, no, or we would pull the build length, and then we would extract the maximum value. So this is another note on our coding and live coding is that you make sense, and then you want to extract the maximum value with NA remove equals true. And then it will give us this, right? So you are getting the data set into shape. You're telling it, okay, I really just care about this vector, and then I just care about the maximum value in this vector, right? Pipes, so like I do this step, I pass on to this step, I pass on to this step, I finish with this one, right? Now, there are many Dplyr functions. There is something like slice, so you can subset rows by, instead of saying, oh, I want to filter, you can say, I want to keep row 1 and 5. You can use slice. You can use pool, so we use pool to extract the vector, right? So we did that just earlier, right? We can use pool, you can use count and distinct. So distinct will return a vector of the different species. Instead, count will return you a count of those different species, right? You have many more. Now, this is something that I wanted to put out there for you so that you can consume it on your own. And it's the idea of merging data frames, right? Sometimes we work on the basis of one data table. But many times, as our data science projects become slightly more intricate and complicated, we might get some data from this data table, and then we're gonna use auxiliary data from this database, and maybe there is an API that is feeding data from another place, and then we need to merge this, and this is where joins come in. So maybe you all might be familiar with pivot tables in Excel or something like this. These are ways to join those tables and merge them, right? So there is inner joins and outer joins. Those are the two general operations. And then you can take a look at these ones in here. The exercise that I am using for illustration is working with flight data. So these are flights that arrived, I believe, is in airports in New York, right? Arrived and depart, and it has a data set of almost 350,000 departures and arrivals from JFK, LaGuardia, Newark. And then the idea is that you have sort of to some extent database format where you have different data tables that can be connected with keys. And the challenge in here is joining those data sets that are in containing different information that are relevant to this flight. So one data table has information about the actual plane. So who made the plane, what was the capacity, what year was it made. There is another data table that is about the flights, and the challenge is then to perform the joins, get an idea about how the joins work, why we need to use the keys, how to use keys, and then maybe doing some little challenges there that you will see here. Now, the second package, so those joins are also part of the Dplyr package. The second package that we're going to see now is going to be the tidyr package. The tidyr package is a package that lets us transform our data. The two most common use cases for the tidyr package are these two functions right here, pivot longer and pivot wider. So this is the equivalent of transposing your data. You might be familiar with transposing, those of you who are working in different programming languages. There are many functions that are just called transposing. And these functions right here help you turn data from wide format into long format and from long format into wide format. Why does this matter? Because if you remember, the building block of the tidyverse is tidy data. Now, there are different ways in which we can represent the same data in tidy format. Now, there is the longer format, the wider format, and they can contain the same data, but some packages in the tidyverse might expect data in a longer format so that plotting is easy. So in here, the most common use case or the most common package that we will use that will expect long format, where one row is one observation is ggplot. Because when you're doing the mapping on a visual space, it will expect that each observation is one of the things that it needs to map, right? Then we're going to see some of these separate functions that will split things into different columns or include different rows. So let's look at what we mean by wide and long formatted data. So these two data sets that we're loading right here, they are the same data, they're just different representations of those data. They contain data of 4 capitals in Europe and their population across different decades or on the specific years rather of those decades. So in this case, we have Berlin, the population in the 2000s, 2010, and 2020, right? So maybe we can print it in the console so that the data is visible here, right? So you see it, population 2020, 2010, and 2020. All the values in here are numbers representing inhabitants in millions, right? Now we have each row representing city,
Sebastian, I think you're muted.
Can you hear me now?
Yes, thank you.
Can you hear me now? Okay, excellent.
Yes.
That's odd. Okay, so let's go back. So we have these two equal representations of the data. They're the same. We just have different means of conveying it, right? In this case, we have the year being this understanding that we have as humans that these numbers represent years and these numbers represent populations in millions, right? So in here we have the population for Berlin in 2000, population for Berlin in 2010. In here we have the same information. It's just a different representation. Now, sometimes we get data in this format, and when we want to do plots with ggplot, when we want to do statistical modeling, say you want to run some more complex models, it's likely that you would need to turn it into longer format, right? So the way you do this is with this function pivot longer, and it lengthens data. Now, it's totally fine if you don't get it on the first go, because Hadley Wickham, who is the person behind, or one of the main persons behind the tidyverse, and I believe one of the persons even writing this function and maintaining it, he, whenever he gives these introductory talks, he says that he always has to Google what goes where in these functions. So it's totally fine. If this is not super clear, you can always Google. There is also a cheat sheet here that you can use to see what you need to put where and what does what, okay? So the logic when you're creating the new long data frame, the syntax is you input your wide data frame, you tell it the columns that you want to pivot, and then you tell it from those columns, grab the names of those variables and put them in this name. This is going to be the new variable that you're going to create. In our case, it's going to be the year construct. The names are going to be the year, and then the values are going to go to value, whatever you want to call it. So if we wanted to turn this, we're going to grab the city-wide data frame, right? The one that has the wide data frame, and we're going to tell it pivot longer, grab the three columns population 2000, population 2010, and population 2020. Other things could work, right? Like we learned about negative indexing. So everything but city in another way, or even starts with population underscore. There are many ways in which you can do this tidy selection. Then we're going to tell it names to year and values to population, right? And if we run this, we end up with something like this, right? Like maybe it's better if we do it here, so that like we can all see the output better. Right, so you see we have now city, year, population. Now, something that you will see is that if you go again on the vignette, the part that explains, these things have multiple helper functions, right? So you can do something that we write here. Well, like this is not very nice, and pop underscore whatever is not really what we understand as years. So maybe we can do something like the names prefix, and it will remove that prefix pop underscore, right? So you have many more helper functions that you can use, and that will then enhance the way you can engage with these ones, right? So again, when you're doing the lengthening, that is transposing into a longer format, right? You use the columns that you want to transpose, where that's the most basic form, where the names go to and the values go to. And then there is a whole plethora of things that you can add on top of this, right? So in this case, names prefix makes sense. So we remove this pop underscore, right? And then we end up with a cleaner data output. Now, pivot wider, the syntax is relatively similar, but instead what we're going to be doing here is turning this wide data frame, the long data frame, into a wide data frame. So the syntax is long data frame, the IDs, so the columns that are going to be the key to maintain, where the names go to, and where the names are coming from and where the values are coming from. So let's take a look at this. We have this data set, right, which is the city long data frame. And what we want to do is we have city, that's our ID. Like we have these representations of populations of Berlin, Rome, Paris, and London. That's going to be our ID. We want to grab the years. This is going to be our column names. And then the population, whatever lives here, this abstraction of population in millions is what we want to live inside the values of those things. So again, this would be city long df, then the IDs will be city, the names from year, and then the values from POP, and then the result would be the lengthened data set. Now, you see here that we just have the numbers. If we were to ask for the pivot wider, we can see that there is also a names prefix bit. So we could even add a prefix here that is going to do exactly what we had done in the past, but this one is going to add a prefix to the data frame, right? So now we have that, right? So again, you have the most basic vanilla version to engage with this would be names, values, and an ID, but you can add, again, all these types of things, all these additional arguments, and many more. Okay, so that's that for what we have with tidyr pivoting, and then we have things that are also part of tidyr. Again, tidyr has many helpful functions. Some of them can be very useful because like sometimes when we as data analysts receive data, those data are a bit messy and people input it in weird formats. So for instance, in this case, say you receive this data, right? And this is a data frame that has a vector or a column that has the names of people, right? In this case, there are names of economists, but things you're working in your mid-size NGO, you received some logs of the participants of a project, and someone inputted name and surname separated by a dot. How could you separate this? Maybe you want to keep a column that is the first names and other one that is the surnames. Well, there is this function, it's called tidy separate wider. So again, in here comes the logic of wider and longer formats. And then in here, we would grab the economist data set, right? We would grab and tell it, okay, grab the name and whatever is separated. So this delimitation argument by a dot, separated and put the first thing that you observe into this new variable that is going to be called first name, and the second one into the one that's going to be called last name. And we would end up with something like this, right? So again, this is widening the data, right? This is widening the data. Now, there is also a separate, so when would you use this? You have one variable that holds values that need to be separated by some delimitator that is consistent. Now, sometimes a single cell contains information that you want to separate into their own roles, right? So we have Jack and Jill. Jack is a homemaker, and Jill is a philosopher, a philanthropist, and a troublemaker, right? Well, maybe we want to analyze this data. We want to do some statistical analysis. We want to maybe do some nested modeling, something of the sort. Well, Jill actually has 3 roles that she plays, right? So what we want to do for analysis is break it down and make it into a longer format. There is also a separate longer version, and it's called separate longer delim. And then again, the logic is, so we have jobs, and we tell it from jobs, grab the column occupation, and separate everything that is with comma and white space. And what you're going to end up with is the lengthened data set. Now, this is, of course, 2 very random functions that I wanted to use to illustrate that if you have a data analysis problem, if you have a data analysis challenge, it is very likely that many people have already encountered this problem in the past, and they have already written the code, pre-packaged it, made a function, made sure that the function is stable, put it into the repository so that you can use it. Right? So these are common tasks that you might need to do. If you do this manually, right? Like I know people who are not familiar with this type of tools, even if you don't go into a full-on data science role, if you're working for your organization and then you need to work with an Excel file, well, you can copy and paste and create different roles, or you can leverage these tools to make your life easier, right? When do we use separate longer delimiter? Well, one cell contains multiple values separated by a delimiter, and you want one value per row. So again, our packages, we spoke a little bit about them. Remember, again, I want to have this nugget in your head. Install packages always goes down here, right? There are a plethora of packages for R. Someone asked in the Q&A, okay, do you have a list of packages in R? There is a repository that's called CRAN, and it has all the packages that have passed a review process, right? So those packages are created, they go through tests, they make sure that they work on every machine, right? If you're working on Linux, if you're working on Mac OS, if you're working on Windows, they make sure that the things are consistent, the output is consistent, and then they get, to some extent, logged in this repository. They're quote unquote peer-reviewed packages, if you may. You can also distribute your own packages yourselves and hold them in a repository. So this is the case of packages that live in GitHub, right? For instance, you can use a package to create memes. And this package is not in CRAN. So you see in here, the package is not published, but you can create memes in R, and you have packages for effectively everything. And this package you would install not by using the regular install packages, but when packages are not in CRAN, you would download with DevTools and install from source or install from GitHub, right? If you try to install packages that are not in CRAN with the install packages, you would get an error, right? So the whatever name of your package is not available in R, right? So just so that you know that sometimes you might go install a package and it says, oh, error is not existed. It might be that the package is not peer reviewed. It might be a fully functional package, or it's a very specific package that someone created a set of functions for that one specific type of model that is now state of the art in your field, whatever it is. That might live in a GitHub repository. You might not be able to install it with install packages. You would need to use a helper function to install it from whatever repository. Now, we have roughly 25 minutes to talk about my favorite package in R. And that's sad, but it's okay because you can also consume these materials in the future. And it's ggplot. Now, ggplot is by far the most popular data visualization package in R, and I want to think it's one of the most powerful data visualization suites in the world. It is an implementation of a philosophy of plotting. This is known as the grammar of graphics. So there are people who think about the visual space very closely, and they think about how to convey information properly and so on. And there is a scientific endeavor to optimize visual communication. And this package uses that, so GG, grammar of graphics, it uses that syntax, that logic of creating visuals as the underlying basis. So this is my poor man's description of what the grammar of graphics entails, and is that we are deconstructing the structure of graphs into layers. So if you think about a graph lives in a two-dimensional space. But if you think about it in terms of layers, you can add more than one dimension into that dimensional space. You can think of color, you can think of size, you can think of many little bits that you can tweak that can still, within a two-dimensional space, convey more dimensions of information. What do we want to do as data scientists, as policy analysts, as people who are working in industry? We want to make sure that our visual communication is clear, it doesn't misguide, and it concisely presents the point that we want to present. And that's why this logic of the grammar of graphics is so powerful. So if you think about the uncompressed two-dimensional space, we can break it down into layers, and we're going to see these layers into code. And this is sort of the building blocks of a ggplot. And in here we have the basis is the data, or are the data. The data are the actual things to be plotted. Then we have the aesthetics, and the aesthetics are the scales onto which this data needs to be mapped. In R, we have in the grammar of graphics and ggplot, we have the geometries, and the geometries are the shapes that are used to represent the data. So do I want to create a line plot? Do I want to create a bar plot? Do I want to create a scatter plot? All these representations of the data that are on the aesthetics and on the data itself, they are these geometries. Then we have some other things, right? So the facets, if you want to have more flexible plots with different columns, different rows, the statistics. So if you have statistical models or summaries that you want to include in this visual depiction, visual presentation of your data. And then the theme, everything that is non-data ink that goes into your plot is part of the theme. So, oh, I want the legend in the bottom. Oh, I want to use this font from Google Fonts that I really like, or I want to use the colors that are specific to our brand from the Hertie School, or I want to use this particular font type that goes along the things that we use in our company, right? So all these different layers map onto what we do in ggplot. So the building block of our plot are the data that we intend to map. So in ggplot, the way we specify the object, the data frame where our data lives, is the main call function ggplot, right? So inside this function, you would input the name of your data frame. In the future, you will learn how to combine multiple data sources, so you can have a plot that grabs a little bit from this data table, a little bit from a subset of this data table, a little bit from some other data, maybe some summary of statistics or something like this. You will learn this in your Intro to Data Science course, those of you who are joining the MDS. And for those of you who are not and are part of the broader public, it's super nice that you're here. And maybe you can go on the materials, all the materials also for our courses at Hertie, the Intro to Data Science, the Causal Inference courses. They're open to the public. So if you want to maybe follow along what students will do through the semester, you can access those materials and you can see how you can integrate multiple data sources into a single plot. For now, we will work under the assumption that we have the one plot. It's going to be the one data frame is going to be the penguins data frame. Now you have the aesthetics. This is the second building block. And the aesthetics are effectively the mappings of our data, right? So at this point, ggplot will know, I know that you want me to use the penguins data set, but what columns should I use and what should I use them for? And then in here is where the function AES, standing for aesthetics, will come in handy. And this function goes inside the main function call, right? So you have ggplot, the name of your data frame, then you have a comma, and then the aesthetic function that has the arguments, right? So for instance, if you want to have X and Y, you can have X equals your X-axis variable, Y, your Y-axis variable. If you want to have labels, colors, size, all those arguments can be inputted in here, right? So if you think about a two-dimensional space, you can add more aesthetics representing further dimensions of the data into this plane, right? Size, color, fill, this is to name but a few, right? Then the most basic plot, this would be already a plot that will render, would have a geometric object. This would be the third layer. This would be the vanilla version of a plot. It would have a layer to render the graph with a geometric object, right? If you remember, so we had the pipe operator in our Dplyr, in our tidyr, in all this syntax. In ggplot, to add layers to the plot, we use the plus sign. So we have one layer and we want to add another layer, we do it with a plus. So say we have in here, we want to build a scatter plot. That's the geometry point. You have ggplot, name of your data set, something on the x-axis, something on the y-axis, and then plus geopoint. Then you have all the, like, these are the 4 building blocks that we're going to see today. Maybe as you move in the future, you can start playing with more of them. You can also look at Andrew Heiss's data visualization course. He goes also to a great extent into like communication and creating very cool plots. Now in here, this will be a plot with more attention to the non-ink, right? So you have X and Y axis with some data, you create the scatter plot, you put a theme that you want, so pre-packaged theme, and then you give it some names to the labels. So on the X-axis, you want to give it a name that you want displayed. On the Y-axis, you want a name that you want displayed. So in here, we're going to use the penguins data set again. And what we're going to do is create a scatter plot of the length of the flipper and the body mass of the penguin, right? Visualizing is also super helpful for even exploring the data, right? Like you get data that you want to use. You want to get a sense, okay, I want to analyze this data. What's the distribution? What is what values are there and so on. So for instance, in here, this is a classic plot that you would do to maybe get a sense of relationships, right? So this is going to be the first plot that we built in ggplot, right? The default plot then will have on the x-axis and on the y-axis, the labels would be the names of the variables. It would create the scatter plot, right? So this is the geometry point, and by default, it has this very visually pleasing gray background. We will talk about how to get rid of it in a second. So there are many things that you might want to plot, right? So you can plot distributions, you can plot relationships, right? So when we're thinking about plotting distributions, there are plots that are better suited for some things and not others, right? So when we think about plotting distributions, we can think about plots like histograms, like bars, like density plots. So the geom histogram, for instance, works in a way that you have a single continuous variable and it will be dividing the x-axis into chunks and bins and tell you how many values live within those chunks. So by default, it goes into 30 bins. So this is a histogram, right? So it grabbed the whole distribution, the whole spread of the weights of the penguins, divided it into equal bins of 30, and it tells you, okay, there are, I don't know, let's say this is 3,700. There are 25 penguins that we have in this data set with that, within this range of values, right? You can have a geom density, and what it does is that it computes and draws a density kernel. So it is effectively a smooth version of a histogram, right? So it tells you effectively this is how the distribution looks like of the value. So we see a rightly skewed distribution. You can do geom bar, and geom bar renders plots that behave similarly to the geom histogram, but they treat the values as unique values. And geom bar, as in difference from histogram, it's not only constrained to one dimension. So you will see what I mean by now. So instead of telling you, oh, within this bin, you can see these values, it tells you, oh, well, there are, I don't know, let's say this is 2,400 or whatever it is. There are 2 penguins, or 1 penguin rather. There is 1 penguin that has this value, right? So that's the difference between histogram and and the bar. Now let's go back to the histogram, for instance, and see what other things we can do. Histogram. So say like in here, we have, we encourage you to play with the bits, right? So we can tell it, can you change the bin? So instead of it being 30, we want to tell it, can you make it 15? Right? So it changes the automatic binning. You can also put something like, yeah, like let's do fill by this right here. So it will fill with that number. When you have these shapes that have an inside and an outside, you can also use color, and then color would be doing the there is something in here that, okay, yeah, I forgot the equal sign. It will do the outlining, and you can see already that it takes colors in hex code and in natural language. So you can see there are some colors that it knows, there are other colors that it doesn't, or you can just go on Google and play with the color picker and be very flexible in the types of colors that you want to use. Now, when you want to compare groups, you can use something like this, so like a box plot, right? So say we wanted to look at the distribution of weight clustered by species, right? So we know, of those of you who know a little bit about penguins, there is one particular species of penguins that tends to have larger penguins. That's the gentoo penguin. We see it here. So this is the distribution, and then Chinstrap and Adelie penguins tend to be relatively similar in their weight. Now we can also plot relationships, and this is a nicer version of what we did before, where we take care a little bit of the aesthetics, right? So we're having in here some statistics added to it. We're changing the default theme. We're changing the labels to be more meaningful and not just the basic variable names. So if you see, what we're doing is we have the X and Y axis, we're adding yet another dimension. It's going to be the species. So now the species is has its own color. We're telling it, okay, now give me the points, right? So make a scatter plot. And in here, we're creating another geometry. This is a geometry that creates a line of best fit. So it is effectively running a little OLS line inside clustered by the species. And we're using this argument to just remove the uncertainty band. So by default, it creates it with this uncertainty bands. It's okay if it has it. This is a prepackaged theme that we're using, is the theme minimal. So instead of having the background like this, you can use prepackaged themes. There is a theme for the economies. You can download packages that have themes that make your plots look like the New York Times. You have many, many more. And then in here, we use this labs function to change the labels to be more meaningful rather than body mass, grams, and species. Now, something that is cool about this is that it runs sequentially, and also that a lot of the things that you want to do as a person creating graphics is that you want to think about your plot and just implement, right? And this is what I was pitching about earlier when I was talking about the tidyverse, is that many things just mimic the way we speak as humans. Like, you don't need to have cryptic programming, things that you have to memorize, because say, for instance, well, I don't want this thing to be here, but I want it to be in the bottom. Well, like, guess what? The thing to move it is just something that you would say in natural English language. That legend, right? The legend position, put them in the bottom, and you would go in the bottom, right? Like, of course, in here, I am giving you a little bit like dipping your toes in this, right? But the idea is that with this very basic understanding of ggplot, of the grammar of graphics, of the different things that can come into play, you can then extend your tool set. Now, I introduce you to the very basics of my favorite package in R. The best way to move is experiment. And as I made in the pitch earlier today, the R community is super open. And something that I like to do and help me a lot in thinking about how to convey visual information is participating in the Tidy Tuesday social data project. So in here, R and other programming languages, if you're working in Python, in Julia, every week there is a data set released, and people from all over the world share their visualizations. People do it on Blue Sky under the Tidy Tuesday hashtag. There is also a Discord and a Slack channel where people are doing it, and there are people from all different levels of expertise. But also something cool is that people, in addition to sharing their visuals, they also share their code. So for instance, in here, we can take a look at some of the things that people have done here. And you can grab this code that they have shared. There is one that I particularly liked. I looked at this today. But let's think about what people do with the Penguins data set. So this is Cedric, and he's an incredible person who's also teaching data visualization workshops. And with this data set that we were playing with, right, like he creates this very beautiful visual, and then he shares the code, right? So the code is in his GitHub. There is also, let's see, for instance, in here, I imagine that the next one is going to be something pretty cool. All these things can be created with R and ggplot. This is Georgios, and he's one of the best persons to follow if you're interested in data visualization. With the plot that with this data set that is a very toy data set, he created this beautiful thing, and then you can go here and you can see the code that he used, or he changed his Tidy Tuesday thing, but you can see everything that he has created, and you can see every plot that he has created. He shares the code, and then you can adapt it. For instance, I am a very avid cyclist, and I have seen this plot a couple of years ago, and this is a data set that was shared that had every space walk in the history of humanity. This is, again, all created with ggplot, and then it has every person that went on every year, and then it has the length of the space mission. And what I did was just copied the code and then had every ride throughout the year, how many meters of elevation I gained, what type of thing I did. And this is sort of how I spent my last week of the year, playing with data and getting off the work and doing data things. There is also a data science advanced calendar, so you can all play with it, right? You can have different challenges, and with the data science advanced calendar comes in the next call, and it's, of course, these challenges happened already, but maybe you can use them to start practicing these things. There is also a curated list of everything ggplot here. So in here, there are the people that you should follow on Mastodon or Blue Sky. And in here, you have all sorts of packages that you can think of about things that you can extend. So I am, for instance, a political scientist, so you can see there is a package that helps you already create plots about parliaments, right? There is a package that, for some reason, makes you turn every geometry into a cat, right? So coders are silly people. There is a very nice community. You can all be part of it. Don't be afraid to be active, and then you can bring your R skills from very little to very high in a relatively short period of time if you engage with people, if you ask questions, and so on. And there are, of course, very more serious things. Also, I don't know, there are things that if you're working in your company, I don't know, there are things that are useful just so that you show very nice things to your in your company, right? Like you want to create a Gantt graph, you can create these graphs in art. They're nice, they're appealing. If you want to show this in a report, of course, it makes things look nicer when you're doing things for work. Now, there is bonus content in here that you can use to continue working on your skills, right? So there is a portion on thinking a bit more closely about lists, and that's linked then to writing your own functions, how the basic syntax of R looks like, and how we can write our own functions to just avoid repetition, how we can write conditionals within functions. There are some activities you can play with these. There are points on iteration, how you can use loops. Maybe loops are to some extent complicated. Maybe you can use then another package for the tidyr that has looping in a more intuitive way with the map functions. There is a lot of content here that you can scroll to play, talking about debugging, how to solve problems, how to go through this very core part of programming that is trial and error. And then also, again, I want to encourage you to access these open materials, both from the broader community, but also from us at the Data Science Lab. We make our materials open. You can see the slides from the lectures. Many of our professors are sharing their slides. The tutorials, like everything that is R, you can just download them, play with it, and get a sense, also opening this knowledge to all of you across the world, so that we can make, again, something that we mentioned at the start of the session, right? Like the idea, and this is something that we mentioned, and at the core, what we want to do here is to bring these data science skills to the broader public for the common good, which is a core tenet for us. So this is 4 hours of intro to R. I hope that you all get something from this. Again, you will get all the materials. You can watch the videos. They're going to be on YouTube for eternity, unless Google decides that they're going to do something with this. But you can access these. Google things, look up for tutorials online, go into the site of Cedric, of Georgios, to see the data visualizations. Look at Andrew Heiss's site, look at the R for Data Science book by Hadley Wickham and colleagues. And I'm happy that you start this data science journey today. Then in the next sessions, you will learn how to work with Python, you will learn math, you will think about designing experiments in the digital space, and so on. So thank you so much for being here. This was a very nice experience, and I hope that you all have a wonderful week with everyone in the Data Science Lab.
Thank you very much, Sebastian, for a very insightful workshop on R programming for data science. I hope everyone has learned something useful for the start of their journey into coding and data science as part of the summer school. And the next sessions will be on Python programming for data science, which will take place tomorrow at 9 a.m. Berlin time, as well as very similar to today. We hope that many of you will also be able to join us there, because I think I've seen quite a lot of questions on R versus Python. So I think we'll see tomorrow on how each language has its strength and weakness as well. Thank you again, Sebastian. Thank you everyone for joining, and have a wonderful day.